Welcome, everyone, to this portion of the uh, Center for Quantum Networks Winter School. This is the lecture on optical transmission systems for quantum networks. My name is Dan Kilper. I'm from Trinity College Dublin. And with me is Shelbi Jenkins. Shelbi, do you want to introduce yourself?
Yeah, Shelbi Jenkins. I'm from the University of Arizona, ECE department.
Okay, great. So, so Shelbi and I will be taking you through this material and trading off a little bit, and also trying to address your questions and so forth in the question and answer section. Okay, so first off, before we begin, I just want to mention quickly. So, this is a somewhat unusual session of the winter school in that I'm actually not from the Center for Quantum Networks. I'm from the Connect Center, which is a Science Foundation Ireland Center for Future Networks and Communications. And our center actually looks at optical, wireless, and data communications across a wide range of applications and different types of networks and problems in that space, from 6G to IoT and cloud. And most recently, we've been getting into quantum internet technologies. And we're a fairly large scale. We're 11 universities, over 50 funded investigators, and 19 PIs and 250 researchers. So, what's exciting is that there's a program between the US and Ireland that allows for centers to collaborate together. And so we got together, actually, along with the IPIC Center here in Ireland, to work with the Center for Quantum Networks, and in Northern Ireland, the QTech Center with Mauro Paternostro. And so it really creates this nice large ecosystem of folks working on the quantum network problems. And the project is Convergent Quantum Research Alliance in Telecommunications, or CoCreate. And just to quickly mention, so the goals here, so first off, foster deep collaboration between quantum and classical networking communities. On our side of things, we're mainly folks working on the classical side, and we're trying to understand these problems in quantum networks and to work with CQN in order to see how we can develop classical networks that can deliver the functionality and capabilities in order to support these quantum networks. And also then to bring center scale research to critical interdisciplinary challenges for terrestrial and satellite communication assisted quantum networks. And these are some of the topics that we've been looking at in this project. So the course today, what we'll do is, first off, give a brief overview of classical and quantum networks, and then we'll get into fiber optical transmission, fiber transmission fundamentals, and quantum signal issues in fiber transmission. And actually, similar to if you caught the course that Don Towsley and Mateus had put together yesterday, which was really good, looking at kind of classical data networking and then how that relates to quantum data networking. So we're taking a similar approach here, although I come from kind of an experimental background, so we'll be getting into a lot of the kind of hardware and those types of details. But we're going to go back and forth between sort of classical and quantum and try to relate those two and understand how they fit together, and also if we can learn from the classical as we move forward with the quantum. Now, we'll get into network designs and architectures, in this case, optical network designs and architectures. And we'll look at optical system control and management. And I'll briefly talk about quantum systems and coexistence, and review some field trials and testbed experiments that are relevant here. Okay. All right, so first off, some observations. So quantum optical networks are, first off, that any quantum network more than a few meters in dimension will be an optical network, right? There is a possibility to build networks with microwaves, and some of the quantum computing folks that are working in that space with the superconducting qubits and so forth, they're looking at sort of microwave waveguides to allow things to stay in the RF, because it's hard to convert between RF and optical, and if you're dealing with quantum systems. But if you want to go more than a few meters, generally you have to convert or transduce over to an optical signal. And quantum optical networks can be standalone, so you can create a fiber network that just has quantum signals in it, or they can be made to coexist with classical optical networks and share some part of the infrastructure with the classical optical networks. And then lastly, quantum optical networks will need classical networks in order to operate. All right, so there's many different functions and operations that these quantum systems need that basically you're using classical networks in order to make that happen. So, so this is really kind of the main emphasis of this talk, is that we're going to dig into these three issues here, right? So we're going to look at optical networks as they relate to quantum networks, and then look at this issue of, well, what makes sense for a quantum optical network to be a standalone network versus coexisting with classical networks, and what are some of the challenges associated with that coexistence, and then how classical networks might be used to help operate quantum networks, and some of the challenges that we need to address there. And also, if we can learn from where we are in the classical networking space, how we do things in the classical networking space, that can give us some insights into how we might implement things in terms of quantum networks. Okay. All right, so optical communication systems. So there's many different types of optical communication systems. There's what we call long-haul optical transmission systems. That's a picture of a chassis frame from a system that used to be in my lab. And there's fiber optical switches that have fiber inputs and fiber outputs. That's an example in the middle there. In a metro system, typically instead of the large chassis type systems today, they're using these sort of pizza box systems or smaller chassis systems. And they would be a similar architecture to today's long haul systems. There's a fundamentally different type of system, which is the PON system or passive optical network. We'll talk about that a little bit. And these are used in access networks. But again, it's kind of a rack of different components that are plugged into some sort of chassis. In data centers, obviously, we have optical networks in data centers connecting servers and switches in data centers. It used to be that servers were all connected with copper up to the top of rack switch, but today many of the data centers have moved to fully optical. The red cables here tend to be optical cables. So those are going to your top of rack switch there. And in general, all the switches in a data center would be connected with what we call optical interconnects. And then, of course, there's submarine networks. There's a picture of a fiber cable ship that would have big spools of fiber that with the cables in it to lay across the ocean floor. There's a lot going on with submarine cables right now. It's a very challenging space for quantum. It's hard to put a cryostat under the ocean and go those long distances. So actually, the way that people look at doing long distance quantum communication is with satellite communication systems. Now, coincidentally, there's a lot happening with satellite communications right now in the classical side of things, right? So you've heard about some of these systems where they're offering actually broadband access networks and basically your cell phone communications from a satellite system, right? And there's these low Earth orbit satellite arrays that people are putting up in order to actually build networks in space. And it turns out that you can use that for quantum systems. So the fiber network today in the U.S., if you look at, for example, one provider's network, this is a little bit older map, but this is a Zayo network. They're a fiber provider, and the different colored lines across the U.S. and Canada there are all examples of fiber cable runs going across country. And the blue dots with the white in the middle would be some sort of data center or key facility that they have on this long haul network. And you can see it's a mesh network. It's quite complex, hooking up various cities around the country. And in general, there's no point-to-point links. We don't have a fiber that just runs straight across the country and hooks up New York and LA or San Francisco or something. What happens is you kind of bounce your way across the country hop by hop, adding and dropping signals along the way, and we'll talk a little bit about that. And carriers have been continuing. So we talk about a carrier would be a network operator that's an AT&T or Verizon, and they build out these large mesh networks over time, connecting in regional and metro networks. So if you were to zoom in on a particular city in this network, you'd see something like on the right-hand side there, where that's basically all the red is the fiber cables in New York City. And the city of New York has had foresight where they mandated at one point that anytime that there's going to be significant road work, that the people doing that road work have to deploy a cable with 1,000 fibers in it. And as a result, virtually every city in Manhattan now has 1,000 fiber cable going across it. So you can see it's this very dense mesh network in Manhattan, and that the other outlying boroughs and areas are also gradually densifying over time. And so that's a trend that's really happening in all the cities around the world, where we're adding more and more fiber connectivity in there. And if you look at any provider's network in Manhattan, they will show the same network that I'm showing right here, because they all share those 1,000 fiber cables. You need the rights of way and this kind of thing, and so those cables are in there. And if we're going to put quantum signals through Manhattan, we would be sharing the same fiber cable somehow. So you'd have to lease a strand of fiber within one of these cables. And I've shown a highlight there of a 1,000 fiber cable. This is actually from, I think, a 1992 paper. No, the reference you just barely see there, but so since the 90s, actually, they've been able to pack thousands of fibers into a cable and do it in a reliable way. And this cable back in the 90s was about an inch across, right? So you could even imagine that we'd have 10 such cables in a conduit, and so have 10,000 fibers. So we have plenty of capacity for growing more fibers in the network and adding signals, even quantum signals and networks in the network. So if we look at kind of the architecture of optical networks today, what we have is typically that Manhattan network, there was a time when it was just a single fiber ring around Manhattan. And then gradually they added to it and added to it. And so typically what happens is you have this kind of metro core ring, and then to that they add these kind of distribution rings with various nodes on there. And there'll be a couple of places where you'll hook up to the long haul network. So usually it's a dual homed type configuration for redundancy purposes. So these purple boxes I'm showing at the top there, those would be connecting across to that long haul network. And then at some point, all these distribution rings, there might be a box that's going to connect to a point-to-point network or a PON network. And with the PON, you're going to be splitting your signal out into many different subnodes. And that's widely used for residential access. So that'd be your fiber to the node, fiber to the home. There's also microwave, what we call backhaul connectivity out to various locations. And so this is kind of the way that networks look today. And gradually, things have been densifying. So we've had more of a dense mesh in the metro core, and that's been moving out to the edge. And we expect that to continue. Yeah. So I mentioned briefly that, so another type of network would be either space-based, or we talk about high-flying platform communications or drone-based communications. So you can have drones, balloons. There are some examples of people putting communication equipment hanging off of balloons. So this is an interesting area of research, and it's one that's particularly interesting for quantum, because you can kind of do these single, very long hops, right? So the losses up to the satellite well, it's only one pass through the atmosphere up and then one pass down, rather than all this loss going through all the different fiber cables. And so, so it's an efficient way to do very long distance communications. And there's a very famous network in China where they've done both fiber and satellite communications between many cities and within metropolitan areas, where they deliver quantum key distribution services over this network. And so that's actually a deployed network that's received quite a bit of attention, and very important development. So, so in this lecture, actually, though, we're not going to get into, you could spend a whole lecture on space-based communications, satellite communications, and so forth. So we're not going to get into that here. So we're mainly going to focus on terrestrial fiber-based communications. All right, so we don't have to repeat in this lecture what you've probably heard in some of the others about why quantum networks. The point to emphasize here is that when we think about in terms of the network infrastructure and the optical networks, there's really three key kind of paradigms of quantum networks that are important to us. One is your quantum key distribution networks, and that has its own unique characteristics, and it's something that is happening right now. Things are being rolled out and are commercially available. There's also distributed quantum computing. So that's the main focus of the Center for Quantum Networks, for example, and where you want to create a network that supports entanglement across long distances. So this is a particularly important application. It's one where, there's many that believe that we won't have the scalable quantum computer unless we have distributed quantum computing, and even that we have optical networks between quantum computers, so that we can have multiple computers that act together as one big computer. And that's a way to get computing at scale. And so there's a lot of interest in that. The IBM roadmap is starting to embrace that approach. They just announced this year this kind of network-based platform in their roadmap that they're going to start moving towards, and gradually go to longer and longer and larger networks and distances. So, and then there's this other category of kind of networking problems in quantum, which is, we refer to it here as internet applications over networks, so synchronization, quantum sensor networks, long baseline telescopes, and so forth. So there are these specialized sort of quantum applications where you get a quantum advantage by using a network, and they usually they're taking advantage of some sort of entanglement, so they'd be similar to distributed quantum computing in the types of networks. But it's good to keep in mind that there's not just one thing that you're going to build a quantum network for, and there are important implications for your architecture and how you're going to engineer these systems, depending on which of these kind of three main categories of applications you'll be looking at. And there's a lot of confusion, I think. So if you say, well, how long is it going to be until we have a large-scale quantum network in the world? Well, in China, there's already a QKD network that's large-scale that's been deployed, right? And we'll talk about in London, they're offering quantum key distribution services, network operator there to customers, right? So in some respects, you could say that quantum networks are already out there. They're operational. They're serving customers and so forth. But then if you talk about distributed quantum computing, entanglement distribution, now people are saying, well, that's quite a bit further out. It's still very much in the research phase, and we'll have to see if there's a breakthrough or when it's going to develop, right? So just want to make sure that we're aware of that and the different issues there. Okay, and by way of introduction, and we'll point you again to, there was an earlier course, The Physics Behind the Quantum Internet, where I believe it was Mike Raymer kind of went through QKD and how it works and some of the fundamentals around that. So I refer you back to that lecture for a very nice explanation of that. A very common thing is discrete variable QKD, quantum key distribution, and that's kind of illustrated in this well-known figure. And then there's also what's called continuous variable. So discrete variable would be polarizers, where you have discrete polarizations that you're going to vary. And so that's one type of signal that you might carry in a quantum network. And then there's continuous variable systems, so CVQKD, and there typically we're adjusting the phase. So the phase is a continuous quantity. Of course, you still choose discrete values of the phase, and you'll set the relative phase between different pulses going through the system. And there's different ways to set up these connections and how you send the signals between an Alice and Bob node in the network. There's also something that we'll talk about briefly. We're not going to get into the fundamentals of how it works, but that you have what's called measurement device independent QKD, and also twin field QKD, which these typically now you kind of take that that middle Alice and Bob figure and you split it into two branches, and by doing that, you're able to effectively double the distance, although not quite. And so Alice and Bob now communicate to a Charlie node in the middle, and by making measurements on the Charlie node, you can get longer distance, and you can still do QKD effectively, and eventually convert that over to entanglement. Okay, so there's a question here: is it experimentally challenging to perform homodyne detection? And that's a relative question, right? So homodyne in particular can be challenging, because if you want to be at exactly the right reference phase, so it can be quite challenging. And effectively, you need a reference, like in the first case at the top there, where you have a global phase pulse that you then split into your signal and local oscillator, and that allows you to basically do homodyne on the receive side, or a relative phase measurement, and that simplifies it quite a bit. So there's all sorts of tricks to it. When you're at the same frequency, you're effectively making interferometers, which are difficult to stabilize. And we'll talk about some of the complications associated with these QKD systems and other systems for stabilizing phase and polarization and so forth. And so I guess the short answer is it is hard, but there's lots of tricks and methods that people have come up with to deal with this, to the point that we have effectively commercial systems that do that. So there's also entanglement distribution. So I should have said, with QKD, most of the commercial systems were using prepare and measure type systems, and it's a low intensity coherent state that you would be sending, and so you're not using entanglement. But if you create an EPR pair, so an entangled pair of photons, for example, then you can distribute entanglement across the network. So entanglement can be considered a resource to be distributed, and you can perform quantum teleportation or use it for QKD protocols also. So the fact that you can do distributed quantum computing and teleportation with entanglement and also do QKD is where a lot of people are really focused on entanglement distribution, rather than continuing to push the current sort of QKD methods forward. And so there's a lot of interest in that. And this was discussed again in detail in the lectures yesterday. I think Don Towsley went over this quite a bit, so I refer you to that. There's also that when photons are distributed entanglement, they can be single rail or dual rail. And so single rail, if you have a qubit memory and it generates an entangled photon, the presence of that photon is the entanglement that you're using. That'd be single rail. Whereas if you fully encode the qubit onto a photon and its horizontal and vertical polarization, for example, then we'd call that a dual rail qubit. And that has consequences on how you're going to engineer the different components that are going to make your measurements in your quantum network. There's also multipartite entanglement, where you have multiple nodes that you would be entangling at the same time so that they're all entangled, or multiple photons that you'd be entangling. And there's something called quantum discord, which is a more general sense of entanglement. There's some interest there in that it's discord is more tolerant of noise potentially in certain circumstances, and discord can be converted to entanglement, and so maybe there's something that you can do with that. And so entanglement distribution, I'll just be brief on this because again, we had really nice lecture yesterday where Don Towsley went over lots of examples and how all this works. But if we have a single hop link, so we have quantum memories, or QM here is your quantum memory, and they're essentially small quantum computers. So you want more than just one memory location. You'd like to have an array of memory elements, and you'd even like to be able to do some computation on those elements. It's sort of like you think about with a classical packet router is a computer. It's a specialized computer for routing packets. Well, in quantum networks, we're going to have specialized computers, or in this case, we often refer to them as memory registers or arrays, that will do your error correction coding, for example, and other sorts of distillation, which we heard about yesterday again. You'd want to do that in the node. And basically from this quantum computer or memory, you send out an entangled photon that's entangled with that memory, and then perform some sort of heralding or Bell state measurement that will then allow you to entangle those distant nodes. And this heralding can be in the middle, or it can be located at either endpoint. And there's a number of challenges for the scheme. So you can lose the photons along the way. If you want them to interfere on a beam splitter to do a Bell state measurement, well, their polarizations have to align with each other, right? So I want to align the polarization of individual photons that are being transmitted over kilometers of distance. Now the fiber has timing jitter because of index of refraction variations in the fiber. So we have to synchronize we have to know when those photons were generated, know that they were generated, and so forth. So there's many different challenges associated with getting two individual photons to interfere reliably on a beam splitter at some distant node. And that's one of the challenges we want to deal with here. And here again, so we're not going to really get into quantum repeater networks, and that was covered in detail in Don's lecture yesterday. This is just an example. It's good to have this notion in your head as we're talking about the different optical network configurations today. So typically you have to entangle here we have Alice and Bob, and there's 3 nodes in the middle. So you could think of a scenario, and this is from a Dahlberg paper, where you basically do entanglement between neighboring nodes, and then you do some distillation to clean it up, and then you perform the swapping operation, and the swapping converts the entanglement between the individual neighbor nodes to the next nearest neighbor nodes. And then you can clean that up again, and then do another swap, and then clean that up again, right? So this combination of swapping and distillation can allow you to eventually create a repeated link over long distance. And one of the things that we want to talk about a little bit here today is what does that mean in terms of layers? How are we going to layer a network? And so people talk about a link layer that might manage and schedule the creation of these entanglement bits. And then the physical layer would establish that entanglement, let's say. What makes sense in terms of doing that type of division. Often there's a lot of coordination between layers. There's something called software-defined networking. Is that an approach that should be used here? We'll take a look at some of this as we go through today. Okay. And then I mentioned that we'll talk about coexistence of classical and quantum signals. So one of the big challenges is we call linear crosstalk. Here's an example from a paper, one of the first looking at coexistence for quantum key distribution signals. So you have your QKD system, the transmitter and receiver at the top in blue, and there's a narrowband filter there to filter out just that bit of the wavelength spectrum that corresponds to that signal. Now you also need a clock to do the synchronization that we talked about. And so that's distributed over the same fiber. And then here they put a classical signal wavelength multiplexed. So that's a wavelength multiplexer that's illustrated there to put that classical data through the same fiber. Now, it turns out that switches and filters, they generally filter down 30 or 40 dB. So that's a factor of 1,000 or 10,000 that you're extinguishing outside of that filter. But if you're talking about something with billions and billions of photons, so massive numbers of photons in these classical signals, and you have to filter down to single photon levels, right? So these are the hundreds of dB isolation that you actually need. Maybe not hundreds, but more than 100 dB of isolation often that you need. So you really need multiple filtering going on there. So we talked about metro and long haul classical networks. So they use wavelength division multiplexing. And typically they'll use two fibers that are full duplex that have amplifiers on them. Now it's not shown in here, but so if this was a classical signal going over some distance, you'd have what we call an optical amplifier in there. And if you were in some of the earlier courses, you would have heard that amplification is an absolute no-no for quantum signals. So the noise from amplification will kill any quantum coherence that you have. So that won't work. So you have to bypass the amplifiers in this case. Now there's another type of classical system that I mentioned, the PON network, and also the point-to-point access networks. These are actually bidirectional fibers that have no amplifiers. So they're kind of interesting, although the PON networks turn out to have quite a bit of loss associated with them. So that's an issue there. Okay. All right, so we have a Zoom poll, our first Zoom poll. Okay, so and this is really just to get you thinking about what we've just discussed and prepare you for what Shelbi is going to take you through. But so what do you think might be the greatest impact of integrating quantum signals into classical optical networks? And can you think of other potential impacts? So each of these are actual problems that people are dealing with today. So number one, restricting the classical signal powers and modulation. So maybe I have to reduce the power on my classical signals in order to avoid that crosstalk that we just mentioned. Restricting wavelength bands of the classical signals. So changing how you're going to lay out your classical signals in order to accommodate the quantum signals. The use of novel optical fiber types, such as hollow core or multi-core fiber, is an interesting thing, and new network layers for quantum signals. So what do you think is going to be the biggest impact of integrating quantum signals into classical optical networks? So can we put up that poll and tell us what you think? So there's a question, what are examples of new network layers needed for quantum signals? So we'll talk about that towards the end of this lecture here. We'll get into some of that. For option 3 in the poll, would you say also that polarization maintaining fibers would be necessary also to integrate? So that's an interesting question, but polarization maintaining fibers. So polarization maintaining fibers sound like a great idea, but they actually are a bad idea. That okay, well let's see the results of the poll here. So maybe can we go ahead and take a look at the final poll? We'll close it out here. Who has control over that? Do I close the poll or?
It's
Shelbi?
closed. You should see it on your screen with the results.
Okay, that's the final result. Thank you.
Yeah.
Thank you. Okay, so everyone can see that. All right, so people are interested in the network layers, and think that that's going to have an impact. And okay, but let me talk about the polarization maintaining fiber. So you would think that I can just use polarization maintaining fibers and keep everything aligned well, but they have this funny property where when you connect to polarization maintaining fibers, it's very hard to get a precise alignment of those fibers. Actually, they do very well, but it's never perfect. And what'll happen is you gradually get these small variations in that connection alignment, and that adds up as you go through multiple connections or splices between these types of fibers. And that turns out to really start to affect the amplitude of your signals. That and you can basically rotate your polarization around, and then the signal will get attenuated when it gets off of the axis that you're looking at as it goes through polarization dependent losses. And so you see signals start to bounce up and down in power and things like this. So there's a number of effects like that come into play with polarization maintaining fiber. I always try to avoid it in my lab when I work with that. So let's see, I'll get rid of the results here, sorry. Okay. So, okay, now we'll talk about fiber optical transmission. So with this, I'm going to hand over to Shelbi. Shelbi, do you want to share your screen or do you want me to control this?
I'm okay with you controlling it. I was gonna also suggest that maybe we give everyone like a 5-minute break since we're shifting gears a little bit.
Okay, yeah.
I don't know how we feel about that. But we can say 9:45, 11:45 Eastern time, I suppose.
Yeah, okay. 11:45 Eastern time. Yep.
All
Okay,
right,
so we'll take a
sounds
quick
good.
break, folks, and we'll be back to talk about fiber optical transmission.
All right. I think it might be about time to get back into it. There are a couple of questions in the Q&A right now. I think a lot of them we'll end up addressing later in the talk. And if not, we'll try and get to them as we go, I believe. But so now we're going to transition a little bit to talk about fiber optical transmission, particularly about a lot of the fundamentals of hardware and how classical and quantum signals are affected by the different components within our network. So the first thing we'll talk about is just basic optical fiber. So for those of you who don't know, here's a very quick description of an optical fiber where, so an optical fiber is a type of waveguide, and waveguides are at their most fundamental, a series of varying index material. Typically, we'll see higher index in the middle and lower indices on the bottom and top layer. Or they'll be symmetric, depending on the types we're looking at. Fiber optical cables, for example, are symmetric and also circular. So the idea is that when you have this change in index, you can get total internal reflection by coupling your light into these, where the light just continues to reflect throughout the cable and you can guide that wherever you want to take it. So there are a couple of different optical fibers. The simplest is a single mode fiber, which is typically a smaller core material, and it's what it sounds like. It only guides a single mode. And then additionally, you can have larger core fibers that are multi-mode that can, like I say, as it sounds like, they can carry multiple modes within their fiber. This image that we've depicted right here is what we call a step index fiber, where there's a very clear boundary between the higher and low index fibers. Index materials, but there's also graded index, where instead of having a very quick transition, you can have a gradient of your index. They work in functionally the same way as step index fibers, but without that explicit boundary between higher and lower index. And then depending on the applications that you're looking for, these will be made out of different materials. Glass is the most common, but some of them will be made out of plastic and Others will be doped with different materials. A good example of that is an erbium doped fiber, which is typically used for nonlinear effects and amplification. But so these are just some optical fiber fundamentals. Dan, if we want to move on, we have some. So some of the important characteristics of optical fibers. The most important, I think, that we'll talk about today is loss mechanisms in our fiber. And there are a couple of different ways that you can, or that loss occurs in fibers. One of the main ones is absorption. When light is interacting with any material outside of a vacuum, it's expected that there will probably be some form of absorption. And that absorption will increase as you increase the length of your fiber. So when we're talking about on the order of kilometers, you'll end up with a lot of loss just from absorption. And then there's also scattering. There's two types of scattering. There's Rayleigh scattering and Mie scattering. Mie scattering typically happens from physical defects within your fiber, whereas Rayleigh scattering is more common, resulting from small changes of index of refraction. And then, so in this middle picture here at the bottom, we can see the absorption of different wavelengths of light throughout across the spectrum. So as you can see, at about 1550 nanometers is where we see our lowest levels of absorption. This is why telecommunications are typically operating at 1550 nanometers. But depending on your applications, it's okay to go to shorter wavelengths or higher wavelengths if you don't need to account for that much absorption throughout your network. And then the next thing that we're going to look, or that we care about when talking about long distance communications in fiber, is dispersion. And there are a couple of different ways, or a couple of different types of dispersion. The first one is a spatial or modal conversion. So earlier when we talked about multi-mode fibers, each of those modes contained within that fiber will propagate at different speeds, which means that the longer your fiber is, the more spread out those different modes will become, and you'll get a lot more distortion in your signal. Same with chromatic polarization. Chromatic, I think, is, at least where I'm from, that's the one that we talk about the most, and that's the dependence of wavelength on your dispersion. So this plot at the upper right, we can see for a typical single mode fiber, as you increase your wavelength, your dispersion will increase. So the longer wavelengths will travel at different speeds than the shorter wavelengths. So when you have multiple signals on one fiber, the longer your fiber goes, the more distortion you'll get between the beginning of the fiber and the end of the fiber. And then finally, there's polarization dispersion. And these typically result from environmental factors, such as temperature or vibrational, like stress on your fiber will cause variations in the birefringence. So different polarizations will propagate at different speeds throughout your fiber. And then finally, the last thing that we care about is bend loss. And this just says that the more bend you have in your fiber, the more likely you are to couple some of that light out of it or scatter some of the light out of it, resulting in overall loss in your fiber. So now we'll do our second Zoom poll. So what kind of signal impairments do you think result from dispersion in optical fiber? The options are it decreases the average signal power, it increases signal distortion, reduces your communication speeds, or increases your nonlinear effects. So we'll give you guys probably about a minute or so. We can share the results. Okay, so the answer to this one was an increase in signal distortion. That dispersion effect, depending on the kind, actually all of them, is going to typically broaden out your signal over the length of your fiber. So the answer was B, number 2. They're all bullet points, but yeah. All right, if we want to continue on. So So we talk about this because we care about loss in our optical fiber, particularly as it is relevant to our quantum systems that we're trying to coexist within our fiber. So here's an example of some work that was done looking at how to extend the transmission length of potential QKD systems. So we can see here from this figure, there are these repeaterless bounds at the bottom, which, correct me if I'm wrong, Dan, I think are supposed to correlate with this yellow B capacity. But as we can see, so these are looking at these twin field QKD systems, which Dan briefly touched on earlier. So we can see that the ideal curve extends out as for longer optical fiber systems. The loss rates, or the rates at which you can get these key rates across your network, is a lot more efficient than with the typical repeaterless bounds that we have. The non-ideal case.
That's right. I think the key here is that just to point out that you're only going to get, around 100 kilometers typically, and in hero experiments you can go out to a few hundred kilometers distance, but at very low rates, right? So it depends on your rate drops off as you go longer distance. Yeah.
Oh yeah, the individual points right there are for experimental data that has actually been performed, which is not specified in our slide, but
we'll talk about more recent results where people have done hero experiments out to 1,000 kilometers.
Wow. So one of the attempts to reduce loss within our quantum systems is integrating hollow core fibers. A hollow core fiber is what it sounds like. Instead of having that high index core material, it's actually it's air, more or less. So one of the main things that we see with these fibers is decreased loss. So here it's showing 0.18 dB per kilometer at 1550. A typical single mode fiber, I think, will generally be about 0.25 dB per kilometer. So they are lower loss. So when you're talking about very long distances, that actually becomes a pretty impactful difference in loss. And the other thing is that since there is no, when you're working with air, the nonlinear effects in air are significantly less than any sort of material. So we don't have to pay as many nonlinear penalties. One of the downsides to this hollow core fiber is that the bend loss is significantly higher. So when you're working with networks that have a lot more bends in their system, this is true for metro networks where you have to go around buildings, or data centers where everything is all within one, office building. These networks aren't going to work as well because there's too many bends, and we're going to end up with more loss than I think we would see with a standard single mode fiber. And then the other thing is that since there is no core material here, we can't use it for any sort of nonlinear amplification, such as EDFA or Raman amplifiers. That's not, I don't think that's typically considered an issue in quantum systems, but when we're talking about coexistence with classical networks, that does become a bit of a problem because we need that amplification for our classical networks. And we have another Zoom poll here. In which application would hollow core fibers provide the highest signal to noise ratio? Your options are within office buildings, in long haul submarine networks, in metro networks, or in data centers. All right, go ahead and end it here. So the answer to this one was in long haul submarine networks. With the other ones in the office buildings, metro and data centers, there's typically a lot of bends. And as we stated earlier, with hollow core fibers, there's a lot more bend loss. So the more loss you have, the lower your signal to noise ratio is going to end up being. So we can move on to the next section here. I think is on polarization. Yeah, okay. All right. So I'm sure it's been discussed a couple of times in previous courses that when we talk about qubits and entanglement, a lot of the time we're looking at polarization entanglement, at least when we're looking at optical systems. So being able to monitor and maintain polarization throughout or compensate for polarization throughout your network is really important. So we have two experiments here looking at fluctuations in polarization over time. So these fluctuations I mentioned earlier typically come from environmental factors. This can be temperature and stress, I think, are the two that we primarily look at. That stress induces birefringence, and change in temperature changes the index of refraction. So we have two experiments here. One of them is looking at, I think, a longer network, 10-kilometer network. And these are individual snapshots of different regions over a 1 second period. So you can see in different places, there's more or less fluctuation in your polarization than in others. And then in this other experiment on the bottom left, this one was actually monitored over the course of 3 days. And this, I think, is really interesting because it shows, especially during the daytime, how the polarization is affected by different conditions such as weather. There's a lot more people out during the day, so vibrations from the roads, which the fibers are typically laid under, cause a lot more issues, and then also increases in temperature from sunlight. And also in this particular experiment, they mentioned something about the first evening that it was there. There was a lot of rain, and the changes in weather during that caused a lot of fluctuations in the polarization, whereas the next 2 nights where the weather was more calm, the polarization was a little bit more stable. So this is just to show that being able to monitor your polarization over time is important, because there are a lot of different there are a lot of fluctuations that happen due to different environmental factors, and it's hard to predict them. So being able to directly monitor them is going to be important for implementing quantum signals into our network. And then the next slide, please. So one of the ways, or there are a couple of ways that people try and model this and compensate for it. One method that people use is to actually break the fiber up and represent different sections of the fiber as different Jones matrices. And Jones matrices, for those of you who don't know, are matrices that can describe different polarization effects or devices. So there's Jones matrices for polarizers and rotators and things like that. So that's in theory a good idea, but you have to be able to break your fiber up into accurate sections and model them. Whereas, but the issue is that when you're trying to do this real time, those different sections are actually, the Jones matrices will look different at different times depending on your environmental factors. So another thing that people do is they will implement optical or electrical compensators, which essentially are just adaptive feedback loops that will, when there are changes in polarization, it'll compensate the opposite direction. And so a lot of the time, or some of the time, what people will do is they will send down reference signals down the same fiber and look at what compensation they needed to perform to maintain polarization. And then theoretically, you can extend that compensation to your quantum signals in order to be able to maintain polarization of that signal. Because as we stated, having consistent polarization from your quantum signals is important to maintain entanglement and fidelity in your network. So this is just one method or one idea of how people are trying to maintain that in these coexistence systems, especially when we can't work with things like polarization maintaining fiber or moving on. Okay. So another important thing that we talk about in optical fibers is timing jitter, which typically comes from, this dispersion when our signal is propagated. So timing jitter is just a variation in the timing or arrival of the signal based on what you were expecting. And these can come from a couple of different things. They can come from instability in your clock synchronization within your network. They can come from fiber dispersion, either from normal dispersion or from nonlinear interference of your signals. They can come from electro-optical conversion at different points of your network, or different environmental factors that would cause a delay in your signal. So we have a study here that looked at the phase variation across time. This is over 60 hours, and then the bottom is just a zoomed in portion of that. It becomes really important to know when your signals are going to arrive in a network. That's true for classical networks, but we'll show in the next slide that it becomes particularly true for quantum networks. So this, in a similar fashion to the polarization compensation, by monitoring the variation in your phase or your phase delay throughout your network, hopefully we can implement reliable methods to compensate for that so that we can keep track of where our signals are and how, or like when they're getting to different places in our network reliably. So as I mentioned, it's important for optical networks to reduce this timing jitter, but particularly for quantum networks. And one of those reasons is that when you're dealing with quantum networks, you're typically going to want to do Bell state measurements and heralding. And I'm sure we've discussed this in other courses, but just a brief overview. We have a Bell state measurement here where you have two incoming photons, 1 and 2, and they'll be in an entangled state. Both of these photons, for a Bell state measurement to happen, both of these photons will come in and they'll interact at this beam splitter. And then if you get a correct coincidence count on the other end, then you can verify your entanglement, or you can herald other signal photons in your network depending on the nature of this Bell state measurement. So we particularly care about timing jitter in these because in order for this Bell state measurement to work out, your photons need to be interacting on this beam splitter at the same time. So if you have one of them that's arriving early or late, you're not going to end up getting a successful Bell state measurement, which essentially is going to be a lost quantum signal within your network. So being able to compensate for that is an important thing that I think people are looking into. But yes. So now we'll move on to talk about some more of the nonlinear effects in our system. The most significant we'll talk about is Raman scattering. So this is just the simple Raman effect here. It says that when you have an incoming photon interacting with material, through this Raman scattering effect, you can end up with a photon of a different frequency. This one is what we call a Stokes frequency, where the input signal photon interacts with the material, and some of that energy is stored within the material, and some of it is released as a lower frequency photon. You can also have an anti-Stokes scattering, where the input signal actually gains energy from our material through vibrational effects and releases a higher frequency photon. So we can see here, this effect, this Raman gain spectra, says that when we have an input pump frequency, The actual gain spectrum from that is going to be shifted a couple of nanometers, or actually typically a couple of 100 nanometers, I think. Tens to hundreds, depending on what you're looking at. So this becomes important in classical networks, particularly for Raman amplification. And this is an effect that occurs throughout your entire fiber, actually. So it happens for long distance signals. So here we have an example of a classical optical network. So at the beginning, we have a ROADM, reconfigurable add drop multiplexer. And this is a device that essentially allows you to pick and choose where your signals are going to go, depending on wavelength. So those signals will all be inserted into this multiplexer, which takes all of them and inputs them into a single fiber. So you'll have multiple wavelengths in a single fiber traveling over a long distance. And as we propagate along our fiber, we end up with a lot of loss. And then to compensate for that, we have optical amplifiers. There are individual EDFA amplifiers, which we're not really going to get into right now because we can't use those, or those aren't particularly important when talking about coexistence with classicals or with quantum signals. But when we talk about Raman amplifiers are actually, the mechanism is amplification throughout your optical fiber instead of just at one point. So that amplification happens along the propagation to the next sort of amplifier system for as many of those as you need in order to get your signal to the other end and maintain your signal to noise ratio. And then that signal is then demultiplexed into different wavelength selective switches so that, or one wavelength selective switch so that you can send different signals and different wavelengths to different parts of your network, depending on your end goals. So when we look at quantum signals in this, quantum signals are typically on the order of a couple of photons. So if you want to insert your quantum signals into a classical network, as Dan stated earlier, you're going to need to bypass those amplifier systems because the signal to noise ratio is going to deplete your quantum signal. And also you can't copy your quantum information in order to amplify it. So, yes. Right. Okay, so when we talk about Raman scattering, there's actually two different kinds of Raman scattering. There's forward and backward. Forward Raman scattering is where your incident light and your scattered or amplified signal are traveling in the same direction. And then for backward scattering, they're traveling in opposite directions. So we have these experiments here looking at scattering within a network. The figure on the left is for forward scattering. The figure on the right is for backward scattering. So you can see that we have a Raman pump signal. I think it's about, yeah. So we've got these WDM channels within the C band, but we can see that from those Raman effects, we actually end up with this background signal in the O band from 250 to 1410. And then similarly for the backward scattering, we end up seeing the same sort of thing with the additional backscattered signal. And one thing to point out for forward versus backward scattering is when you backscatter for Raman amplification, that amplification actually occurs along the whole length of the fiber instead of just a portion of it. Dan, I don't know if there's anything you want to add about this slide or not.
Maybe just to emphasize that you might think that you can avoid Raman scattering by saying, I'm going to send my quantum signal down at 1310 nanometers, which is the other telecom band, and that's what's shown on the left hand of each of these plots. And the unfortunate answer is that you still get Raman scattering even almost 200 nanometers away from your sources of the classical sources. And so it's really hard to avoid no matter what you do.
Right. Yeah. So having those like very few photon quantum signals within your fiber at any wavelength is going to be an issue when you have this Raman scattering effect. Yes. Move forward. Oh, we have a Zoom poll. Okay. So what is one of the biggest concerns regarding Raman amplification coexisting in a network that also has quantum signals? The options are: it creates too much noise in the network, it has too much power consumption, the bandwidth for application isn't large enough, or it is too large. And we will open that one up. All right. Go ahead and share these results. So it looks like most of you said that it creates too much noise in your network, and that is the right answer. Particularly when you're talking about, our very small quantum signals, any competition is going to be likely too much when you're talking about single photon information. So good job there. All right. So yeah, okay. So the next thing we'll talk about is, this is kind of a first introduction of like a true network design. So this is a passive optical network, and passive optical networks are typically used to deliver broadband services to individual users. And as it sounds like, it's made of entirely passive components. So what we have is, at the beginning of the network, we have an optical line terminal, and this is like the provider of the internet. And a signal from then is then sent down an optical fiber and sent to a passive splitter, where it's split up and sent to different optical network units. And these ONUs are what interface with the interface and allow the provided services to make it to the user end. And a really important thing about these ponds is that they're actually bidirectional. So signals will go from the OLT to the user end and then back the other direction. So we'll typically have multiple signals crossing paths consistently throughout this network in both directions. We can move on to the next slide. When we're talking about Raman scattering in particular, that becomes really important because we have forward and backward Raman scattering. So this is a study that actually looked at this bidirectional transmission in passive optical networks. So we can see on the right here, this figure, we have different pulses. So we have zeros and ones on each of these sides. So on each side of this figure. So for the left-hand side of this picture is depicting Raman scattering. So we can see that those signals end up getting noisy. That's what we end up seeing when we have this backward Raman scattering. And then for forward Raman scattering, what happens is there actually a broadening of these quote one pulses, and that leads to a bit of background noise for the zero pulses in our network. Which is ideal. It's not ideal in either case, actually. Yeah. All right. And then, so I think the final thing we'll talk about in this kind of hardware of optical networks is our nonlinear effects. So a nonlinear effect is something that occurs when you have a high intensity signal. Raman scattering is actually considered a nonlinear effect. But there are a couple others. So there's the optical Kerr effect, which says that when you have a high enough signal in your waveguide or your fiber, that high intensity signal can actually change the index of refraction that signal is seeing. So this occurs, one of the results of that is called self-phase modulation, which for this figure on the right, you can see there's a nonlinear pulse of high intensity, and as it propagates along our fiber, it actually becomes distorted just on its own because of this phase modulation. And then there's also cross phase modulation that says that you have fibers, different signals from fibers can interact with each other and change the index of refraction of a different signal. So the different implications of this, or the main one is just crosstalk, which is, it says that when you have a signal from one channel interfering with a signal of the other, it's going to end up distorted, or you'll end up with noise. And that's something that we don't want in our classical networks. So in this table here, we have a couple of different typical fibers and their nonlinear coefficient. And the nonlinear coefficient just specifies for a given field how much of that nonlinear effect you're going to see. And some of them will produce higher or lower nonlinear, or like more intense nonlinear effects. And some of them will be less affected by these things. And then we also have, we have wavelength division multiplexing, which is really important when we're talking about having multiple signals or multiple wavelengths within our network. So what wavelength division multiplexing allows you to do is to include multiple signals on the same fiber at different wavelengths. So you can carry more information at one time that's distinguished via wavelength. One of the issues that we see with that is four-wave mixing, and four-wave mixing is actually a third order nonlinear effect. So it's not as common as the second order effects, such as self-phase modulation that we were seeing in the previous slide. But four-wave mixing is when you take 2 or 3 signals and those interact within a material to produce 2 or 1 additional wavelength that you were not originally seeing. And this is something that we don't, we hope not to see in our classical optical networks, because a lot of the information that we carry is specific, or it's different information is carried in different wavelengths. So if we're seeing changes in our wavelength throughout our network, then we're going to lose a lot of that information. And this is just for, right now we're just talking about the classical sense. But I think in the next slide, yeah. So we care about nonlinear effects in quantum signals for a couple of reasons. Typically, so when you're looking at classical or quantum signals that are on the order of a handful of photons, you're not really going to see nonlinear effects on their own, because nonlinear effects are caused by high intensity signals, and we just don't get that with a few photons. So classical systems that we have today are typically designed to reduce nonlinear effects as much as we can. And this is because, you know, like we said, we don't like distortion in our signal or changes in our wavelength. So a lot of the time people will compensate for these by using lower signals, or trying to affect the signal to noise ratio, which is great in theory, but the reality is that you're probably still going to see some nonlinear effects from your classical signals. And when you have those few photon quantum bits of information, any nonlinear effects are going to end up causing issues with your quantum signals. So that's considered one of the big issues with coexistence of classical and quantum networks. And we don't currently know exactly which effects impact which ones are going to be the biggest impact on our quantum signals, because there are so many different factors here, as we stated, wavelength, power, and fiber characteristics. So we can try to compensate for them, and we can try and account for them, but knowing exactly the best way to do that right now is a little bit difficult because there's so many different moving parts. But it's something that people are keeping a pretty close eye on when we're talking about integrating quantum and classical signals. And that's all we have for the fiber and transmission system. So I will turn it over to Dan now. What about system networks?
Okay, thanks, Shelbi. And there's one question. Actually, there's a couple questions now that are online that I thought I would go ahead and answer verbally here. So One is about, it would be interesting to know how important the requirement of classical and quantum coexistence is to network operators, given that there's 1,000 core cables. So, I mean, there's still a cost associated with leasing a fiber, right? So there's certainly interest in being able to put them together. But to my knowledge, all of the examples where there's commercial hardware involved, there's always separate fiber for the quantum signals, because as the question is leading there, you can always just use another fiber and it's easier. I mean, people do demonstration type experiments to show that you can have coexistence working to some extent. But to my knowledge, and we'll get into some of these field trials of coexistence experiments, but generally you always have to kind of turn down the power on the classical signals in order to make it work. And that's kind of a non-starter for if you're going to really deploy and operate a network. So currently it's not there isn't coexistence, but it's a good research problem, and if we can find ways to make it work, then that's a great thing. But as you just heard from Shelbi, Raman scattering is a huge problem. Although if your distances are short enough, or if you go to hollow core fibers, right, or even multi-core fibers and use different cores, you can do all right. There's another question in there about Brillouin scattering. Does it have some effects in those networks? So Brillouin scattering can be important, but the Brillouin threshold is pretty high. And generally, you know, we use techniques in WDM systems, the classical system, to avoid Brillouin, and by having broadband signals and keeping the power low. So generally that's, and also the Brillouin scattering, I think is it 11 gigahertz or 13 gigahertz? It's like 10 gigahertz away from, it's a shift by about 10 gigahertz. And so normally if you're putting your quantum signal farther than 10 gigahertz, you can avoid the Brillouin scattering, right? So not such an issue. Yeah. Okay. All right, so we'll move on with the lecture. So systems and networks. Okay, so so again, I referring back to Don Towsley's lecture the other day, talking about data networks, different types of data networks. Well, we have an analog of those networks in optical networks. All right, so here I want to talk a little bit about these optical networks and how we might use them in quantum systems. So and there's in a lot of cases, we don't have really formal definitions. So we talk about optical burst switching. And generally that's data sent in unscheduled, unsynchronized bursts. It's a kind of a random access, and there might be control information in a separate channel. Tends to be limited in scale because you get a lot of collisions of these bursts, right? And so you need a lightly utilized network to make that work. There's passive optical networks. So these are bidirectional in the fiber. It's a multicast system. You saw an example of what it looks like from Shelby's slide there. And it's sort of random access, but it has time and bandwidth allocation. So it is you do get scheduled through. There's a head-end terminal that tells all the remote nodes, okay, you can control the fiber now and send your signal at this time, so it allocates time and bandwidth to each of the end nodes. And this is limited to a single hop and only passive networks with no amplifiers, and so about 20 to 80 kilometers. Now there's something called optical flow switching. So this is data sent in scheduled and synchronized but unbuffered flows or slots end to end. So there's no buffering. So that's the difference with packet switching. But you're adding some scheduling and synchronization in there. Generally, you need some universal clock synchronization and guard bands to account for jitter. An optical packet switch network. So here you would have buffering and routing hop by hop to a destination. A big thing here is that there's no optical memories. So there's no optical packet switching. So there currently there's no commercial optical packet switching. And so there's optical circuit switching. So here we have a dedicated wavelength in a WDM system, or you could have time circuit switching channels that are established end to end. So you dedicate resources end to end, and often there's some sort of wavelength or digital wrapper or header that's used for forward error correction coding and clock synchronization on those signals. And it's widely used in a set and forget provisioning mode for networks. So actually this optical circuit switching is what's used, but note that it's used in a set and forget style. So you don't continuously switch these signals down different paths. You actually set it up and then you just leave it there for the next 10 years. And that's the extent of optical switching in amplified networks, anything beyond a PON network. So when we talk about this type of optically circuit switch network, this is what the architecture of it looks like. So typically we're using a reconfigurable optical add-drop multiplexer, or ROADM we refer to them as. And this kind of illustrates it here, that you have amplifiers on the input and output. You have some sort of wavelength selective device or add-drop device that's typically a wavelength selective switch. And then you need something to equalize the channel powers, so dynamic channel equalizer. And it used to be that we'd have dispersion compensation modules in there, shown in this figure. Today with coherent signals, we actually get rid of the dispersion compensation. We don't need it in line anymore. We do it in the transceivers. And then there's we have optical performance monitors that actually measure the channel powers so that we can adjust them with our dynamic channel equalizer. And you can see how we basically multiplex and demultiplex these optical signals and send them over to routers or what's called an OTN switch and so forth. And the wavelength selective switch is a special switch where the easiest way to think of it is I have a grating, that's this red bar on the lower left-hand side here. And then we have some lenses and mirrors, and I have a fiber, the yellow fiber coming in. It sends light through the system, and then the light diffracts, and each different wavelength goes to different mirrors, and then those mirrors can tilt and send the light then to other fibers. So you can select individual wavelengths to go to individual output fibers, and it works in the reverse direction as well. So that's a wavelength selective switch, and it's widely used in optical systems today. It can handle quantum signals as well. So we make networks out of these ROADMs, and so here's an example figure at the top there where you can use a power splitter and wavelength selective switch to construct what we call a multi-degree node. So you come in through an amplifier into this power splitter and send the signals to the different output nodes. And then on the output nodes, you have a wavelength selective switch that's going to block channels that shouldn't continue and allow channels through that should go on. And so with this architecture, you can selectively send your signals down any path that you want. Now, the state of the art here is what's called a CDC flex ROADM, or colorless, directionless, contentionless flex grid ROADM. We don't have time to go into what all that means, but this is kind of the state of the art technology that we have there. The little figure down at the bottom shows, so typically these networks use full duplex fiber pairs on each input and output port. So you're going to send the different directions on separate fibers. You're not going to send them bidirectional in the same fiber. And as the bullets say here, so that no degree can scale to 10 to 20 ports. And networks of thousands of these ROADMs have been deployed over tens of thousands of root kilometers. So they're used all over the place. And typically the fiber spans between amplifiers that are along those links between the nodes. So each of in the bottom figure there, each circle would have something similar to what's at the top, right? Although it would also have some add-drop capability normally. And the distances would be anywhere from 10 to 150 kilometers. And if you go more than about 150 kilometers, you have to put some sort of amplifier in there. Okay. And as Shelbi mentioned, newer systems can have Raman amplification in the span, which is death to any quantum signal. So forget about using quantum in a system that has Raman amplification in it. But discrete amplifiers, you can put a fiber and jump around the amplifier. You can basically bypass it with a filter to go around it. Okay, so an interesting thing is the system vendors who are making these types of commercial ROADM systems today, they're offering QKD and post-quantum cryptography in their cryptography system. So historically, they've always had a cryptography offering for the security of the systems, and they'll typically have a key management service that they offer with their systems. And now most of them, I don't know if all of them, but probably most of them that I know of today are offering some sort of key management service that integrates with QKD. Now, they don't have the QKD built into the systems today, but their systems are made so that you can purchase a QKD box from some one of these vendors that sells QKD systems, and you can then get it to provide the keys for your classical communication system. And these systems, they will have signals at hundreds of gigabits per second, so very high speed systems. But the keys between the nodes for those systems would be maintained and distributed through a QKD system. So that's available today, or it's been under development today by all the different vendors. Now that's huge, right? So this is Adva's, I took from their website. They talk about the quantum safe connect guard encryption, and mentioned that it can support quantum cryptography, right? So and this is the first time that we've seen that offered with commercial systems. So that's really huge development. And commercial QKD systems, there's a number of different vendors. I'm showing a couple of them here, Toshiba and ID Quantique. And they do around a few hundred kilobits per second at 10 dB loss, and you can go up to about 150 kilometers. So you see that 150 kilometers kind of matches that reach that I mentioned for these classical systems between amplifiers. So basically, you have to put these boxes facing each other back to back at each amplifier node and have them hop across. And we do something called a trusted node. There's no repeaters or amplifiers for these quantum systems, but if you trust that amplifier hut or central office where your equipment is, that no one's going to get into that, then you can have your QKD signal terminate there and then just generate a new one onto the next link. So you're repeating it that way. And these they're offered in what's called the telecom C band and the S band. So S is around 1310 nanometers, C band is 1515 nanometers. There's numerous startups and new system variants that are under development and being offered in this space. So it's a rapidly evolving space right now. Now, all of these systems that are offered commercially that I'm aware of are point-to-point systems. Okay, so I wanted to point to this, another interesting development in the QKD world. So British Telecom, BT, they have a commercial deployment in the London area where basically they're acting as a network operator for QKD, and they say they have customers for this network. But basically, again, it's separate QKD. So the QKD signals are carried on separate fibers, and there's no coexistence. But they offer that their customers can basically use these QKD links now to secure their data. And they've been trialing this in the London area now for some time, I think maybe over a year. All right, so that's kind of the main metro and long haul type of systems. We mentioned these PON systems, so passive optical networks that are your residential access, fiber to the node, fiber to the home. So typically you have this optical line terminal, and it's going to have a 1490 nanometer signal going downstream and 1310 nanometers going upstream from the individual nodes. And then you'll have this split that'll do sort of a 1/32 is typical. Some of them go up to 1/128, but 32 would be more common. So that's a 15 dB loss. which actually that's a pretty tough loss to overcome for a lot of these QKD systems, although in principle you can do it in some cases. And you can see that, but all your homes, let's say, in your fiber to the home system are different distances from this optical line terminal when you split out all the different fibers. So the line terminal has to actually measure and determine the different delays between the end nodes. And then it does a time synchronization so that it's able to sort of time multiplex all of these different end nodes and grant them access to the shared medium at particular times and with a particular data rate. And so that's how they work. And so you can imagine, or think about how I can have a QKD system running over that. So let's talk about these quantum systems and coexistence a little bit. So, so this is an example, experiment done back in 2012 by the Toshiba folks, and where they really set a high bar for understanding QKD coexistence. And we showed this earlier. So they put a signal in, a classical signal in with the quantum QKD and also with the clock synchronization signal. And they used narrowband filtering to filter out the quantum signal and basically to filter out all that Raman. So you're really limited by the Raman from the classical signals. And this is kind of showing if there's what they call a CWDM, a coarse WDM filter. And so the Raman flux is the top line there after the CWDM filter. And then with the narrowband filtering, it goes down to the red. And then they do other techniques such as temporal filtering and then they reduce the power of the classical signals, and you get below the levels that you need for the quantum signal, and especially your Raman tolerance. You need to be below that Raman tolerance dashed line, basically, to make the system work. And so they characterize carefully this type of effect. And another thing, so there's been quite a bit of work on this, as we've mentioned, and so this really illustrates in detail these kind of DWDM ROADM nodes that I mentioned with the amplifiers in there, and it's kind of showing how when you have these fiber spans, now you come to these yellow bars. There are basically couplers and filters that are going to split out the quantum signal from the classical signal, basically peel it off with a filtered coupler, and send it to the QKD. And then that can either jump over to around the node to bypass all the amplification and optical switching, or it can be sent over to, and you see OLT and ONT. So this is the PON on the drop side on the bottom of the figure here. And so you can bypass that OLT and put it into the PON system. And so people are thinking about, how can we make this QKD system work with these classical systems? So I put these filters and couplers all over my system and try to deal with the losses that I have on that passive fiber structure and deal with the Raman scattering, basically, is what you struggle with. There's also tricks. I mentioned this kind of time filtering. So people have looked at kind of doing time slotted transmission, and this is kind of they have quantum channels and data channels. So the data channels are the light blue ones in the lower figures there, and the quantum channel is the red one. So in a certain time slot, you're going to send the quantum signal, and other time slots send the classical signals, or arrange them in a way that you minimize the interference effects or the Raman effects between the classical and the quantum. And so people have been exploring how you can play with this. Now, that's really disrupting your classical signals. So I don't know who would allow for that in there as if you're a network operator, but maybe there's specialized applications where you have full control over the system and you want to get some quantum signals to go long distance along with your classical signals. Well, you could play tricks like this. It's also mentioned here that, of course, hollow core fiber doesn't have Raman scattering or nonlinear effect, or is extremely low. So that's promising there. A lot of interest in that. obviously separate fibers works, but also there's multi-core fibers, and you can put your quantum signal down one core and your classical signals down other cores, and that gives you quite a bit of isolation. Okay, so I mentioned that all these QKD systems are point-to-point systems, and that was kind of shown in those coexistence figures. Well, why not have a QKD switch network, right? So I could have basically QKD endpoints. They go into some switch, and it's say an end-by-end bidirectional fiber space switch, and so then I can have any QKD node talk to any other QKD node when they need it, right? So maybe they don't need it continuously, maybe only sometimes, or some communications needs to be secured with the quantum. So so currently there's no commercial system that'll support this, and also currently the systems all use a fixed wavelength. They don't allow you to change your wavelength on there, and the bottom line is that they have very complex stabilization circuits to deal with all those issues that Shelbi was talking about in these fibers. And so that makes it very hard to do any switching, which then changes the fiber conditions, the transmission conditions. Okay. Now, it turns out that while there aren't any commercial systems, of course, people have done this in experiments, and this is an example. The group in China, Jian Weipei's group, did this star network. And they showed that it's actually optically switched in the middle of the star at USTC, which is the university there, to the various endpoints. Now, they don't report any switching time, right? And a bit disappointed in that. And I think that's a critical thing that we need to start to look at in research experiments is what is the switching time, and how can we push that shorter and shorter in experiments, and what does it take to make that work? But this was shown that at least compatibility with trusted node transmission and doing switching. But they talk about that they automatically execute the adjustment and feedback process and wait for the connecting requests from any nodes and choose their corresponding working mode. So, and I think there's a calibration step that they used here where they kind of measured in advance so that they knew what the link was like before they set it up, and then use that information to help with the automatic alignment and things. And I think there's promise there to make this sort of thing work. It'll be interesting to see how that develops. So I talked about optical packet switching and that we don't do any optical packet switching today, right? So so it turns out that we've studied optical packet switching to death, and kind of like what you saw there, where someone's done an experiment for a switched QKD network, although there's nothing commercial. Well, there have been a lot of optical packet switching experiments, but I won't say that there's nothing commercial. So there have been some startup companies and organizations that created actually products of optical packet switches, but they were never really able to take off because they were always fairly limited in their capabilities, usually their scalability, the number of nodes that you can connect and things like that, and other issues that would arise. But the interesting thing is that there's a bunch of different ways that people have looked at being able to kind of do packet or burst type switching. This is a very nice review paper by Ben Yu, kind of reviewing these techniques back in 2006. So it's almost 20 years ago, and there's still been work since then. So it'll be interesting to see if quantum technology can pick some of this up. And in fact, recently there was some work out of Cisco where people were talking about, well, we can use this kind of optical packet switch approach where basically you have header information that is switched away from your data. So you have a main data payload we talk about, and then a header. And you can demultiplex that header away from your data payload. And in the quantum sense, that data payload can be your sort of quantum qubits, your flying qubits, right? And then you can encode this classical information as a header or trailer. So if you look at the bottom of the screen here, so we talk about defining a frame where you have headers and trailer classical data information. Now that header information can be used for making measurements on the line, being able to adjust polarization, things like that, as well as being used for getting routing information on how you're going to manage the network, or you can send information about heralding events or bell state measurement events and so forth. And then you'd feed that on the left-hand side here. So you feed that into your quantum memory and processors. And then on the output side, you would decide where you're going to route the data through this optical switch and where it's going to go on the output. Again, if you saw Don Townsley's talk yesterday, I keep referring back to that. Very nice talk. So he had a similar architecture, but it was for an electronic packet switch. So you have kind of an input stage where you're going to buffer. So you need some memories, and then you split out your address and you do your address lookup. You figure out where it's going to go, and then you set the optical switch and send it out the right port to where it needs to go. You can do all that optically, but you need classical information separate from the quantum. So the classical header information would get split away and processed, and then it needs to be inserted back on top of or in front of the quantum bits that you're going to be sending through the network. This is an intriguing approach that you might imagine could work for quantum networks. And we're talking about memory, so I need a memory. Well, there is commercially available memories now. So QNect is a company in the New York area. They have a rubidium-based EIT memory, and they have a source that uses non-degenerate four-wave mixing to convert between the rubidium line and the telecom band. So they have a nice system there that can work over telecom wavelengths, and it provides both a pair source and a quantum memory that you can work with. So these technologies are now starting to become commercially available. Now, this is at room temperature, a rubidium cell, but scaling to kind of larger numbers of qubits and doing computing in the memory is a challenge. And so if you look at technologies such as NV centers, the color center types of memories, like what it's worked on in the Center for Quantum Networks, those have to be down at cryogenic temperatures. And so there has been a 3-node entangled memory network experiment from the Delft group. Very nice work here, where they basically created a quantum network of 3 entangled nodes, right, connected by 2 fibers. And so I refer you to that paper for more details there. And they show that they could create something called the GHZ state with these 3 nodes, as well as doing a basic entanglement swapping operation. So this is kind of where we are in terms of quantum networks that use entanglement today. All right. And then another type of classical optical network is, well, there's 2 types that I'm pointing to here. One would be a data center type of network. So this would typically be a series of electronic switches connected by fiber links that are just basically point-to-point links between those electronic switches, and also between the switches and the servers. And you'd have those all over in a data center network. It's interesting that very recently, actually, Google announced that they are now using optical switches, fiber optical space switches or fiber switches in their hyperscale data centers to basically help with the efficiency of moving data across the data center network here. And so if you have quantum computers, right? So I have a data center made up of quantum computers, then the question is, how can I create a data center network, optical network that could work here? And then also we can have people are looking at on-chip networks for optical networks to work together with the electronics on chip using integrated photonics. And that's an area with quite a bit of interesting work going on. And also there's potential for developing quantum networks that would be sort of on-chip networks. Okay, so next Zoom poll here. So which types of optical networks use real-time optical switching? PON networks, WDM, metro, and long-haul networks, submarine networks, and data center networks. Okay, so I'm going to go ahead and end the poll in 3, 2, 1. And let's take a look at the results here. So we're talking about real-time optical switching. So data center networks use a lot of switching, but they don't actually use real-time switching. I mentioned that we have introduced optical switches into data centers. To my knowledge, it's kind of, again, in a set and forget type of, or very slow changing configuration. Same with WDM, metro, and long haul networks, very slow changing. But PON networks are the one, actually, that should have been the right answer here, where they use basically high-speed switching because there's no amplifiers. So you don't have to deal with the complexity of changing signals over an amplifier, and the distances are fairly short. In principle, it could also be used in data center networks, but it's not yet. Okay. So let's move on. Okay, so some notes about classical optical networks. So first off, it doesn't matter when bits or photons arrive at nodes, nor what their polarization is. Polarization, as we mentioned, is something that's not well behaved in fibers, so we try to avoid anything that's polarization dependent. Clocks are synchronized after demodulation at the endpoint. So typically there are bits that are sent, optical bits that are meant for clock synchronization. And so that's how we get our synchronization in classical networks. We send them together with the data in the fiber. And data is only read at the endpoints after full demodulation. So we have amplified receivers throughout these classical optical networks. So we only care about what's called the signal-to-noise ratio, or the power, signal power divided by the noise power really drives everything in these systems. We don't care about losses. Well, you compensate loss with the amplifiers effectively, but it's signal-to-noise ratio that you care about because the amplifiers add noise as well as Raman and other nonlinear effects add noise. We have control loops to maintain the optimum launch power into the fiber spans for each channel. So our signals, we care a lot about what power we're putting them in at, and we need to balance between, if the power goes too low, we hurt our signal-to-noise ratio because your signal power is now getting similar to your noise power. Or if you put it too high, you get too many nonlinear effects. So we're trying to find that just right power. And that's one of the issues with, if I try to lower my power to allow a quantum signal in, now I'm going to compromise the signal-to-noise ratio of those classical signals. Now, I might have signal-to-noise ratio to burn there, right? So I could decrease the signal power and still have a high enough signal-to-noise ratio. But you would need to have that available if you're going to use it. And we maintain constant gain in the amplifier. So bits flow continuously, so they're not kind of on off. So we don't do optical packet switching, this sort of thing. The average optical power per channel is basically constant throughout the system. And well, other than attenuation due to fiber loss and then reamplification that way, but on shorter time scales, it's constant. So optical switches are used to configure the system, not to switch bits, right? And they operate on minutes and hours of time scales, except for with PON networks again. So the PON is the one case where you switch bits. Another interesting thing, so classical versus quantum here. So classical networks use fiber pairs for full duplex transmission, with the exception of the PON networks and some point-to-point access networks. So, and this is limited by amplifiers and nonlinear effects. So we don't use bidirectional transmission over long distances because of amplifiers and nonlinear effects. So you don't want to be going in both directions in the fiber when you have a lot of nonlinear effects, because you get nonlinear effects in both directions and they can interact with each other. It's a mess. But on short distances, that's okay. The nonlinear effects don't build up. But quantum systems, well, the power is down at single photon levels, right? So there's no reason not to use bidirectional transmission. So single fiber transmission. So entanglement between two memories can be used in either direction. Now, so when you establish entanglement, now you have that entanglement is basically a bidirectional connection that you've established just by sending these entangled photons across a single fiber. And single photons don't interact in fiber, and there's no amplifiers, as I mentioned. So, and you can use something called an optical circulator to allow for bidirectional transmission. So that's an interesting thing, that bidirectional transmission, it really seems promising for quantum, whereas it doesn't really work that well for classical and long distance communication, especially. Okay, a Zoom poll here. So which of the following is not a problem for realizing high-speed space or wavelength switching in commercial quantum QKD or QKD systems? So not a problem for realizing high-speed space or wavelength switching in commercial systems. So number one, optical switches have too much loss. Number two, polarization dynamics on different paths. There are three, phase, timing, jitter on different paths. And four, complex stabilization electronics and algorithms. Okay, I'm going to close the poll in 3, 2, 1, and we're closed. Share the results here. Okay, so I didn't talk a lot about complex stabilization electronics, to be fair. But the correct answer should have been optical switches have too much loss. So actually, optical switches don't have too much loss. There is loss associated with them, but there are some that have very low losses, and we'll get into that here. But all the other things are problems with optical switching in quantum systems. All of the stabilization, the timing jitter, the polarization effects, and so forth. Okay, a little bit of a trick question there. Okay, so let's get in the next slides. We're going to get into this a little bit about the optical switches. We can look in more detail there and learn something about that. All right. Before we get to switches, though, I just want to mention and give you a picture in your mind of what WDM systems look like, or dense wavelength division multiplexing. I like these figures from Chris Fludger's paper in 2016. So basically, although it's a little bit blurry there, sorry about that. So in this work, they created actually a 1 terabit per second polarization multiplex 16 QAM super channel transceiver in this little CFP2 package, and using 4 by 40 gigabaud. So it's actually a packaged 1 terabit per second super channel. We're not up to 1 terabit per second in commercially offered signals yet, but we're getting close. We're at about 800 gigabits per second right now. And so it looks something like that top left figure. And then these 4 subcarriers for this 1 terabit of data here is packed into the middle of this DWDM spectrum here that has 4600 G channels on each side of the spectrum around this 1 terabit per second signal. So you can see these very high density cramming of these optical signals in it, right? And so somewhere in the middle of this, we'd like to put a quantum signal, maybe, or maybe not, or this is at 1550 nanometers. You look at the spectrum there, it's 1543, 1548, 1553, kind of in that range, 1530 up to 1560. And then, so a lot of people want to stay away from this, right? So the huge power, so the vertical axis here, this is just into their optical spectrum analyzer. They're at -40, but on the line, typically the power of each of these signals is going to be around 0 dBm or so. So 1 milliwatt per channel. The total power of all of this would be over 20 dBm or 100 milliwatts. So that's a huge amount of power that's going to generate a lot of Raman scattering. And so we need to put our quantum signals way down at the at 1310 nanometers, or as far away from this as we can get it. Okay, so now we have those different wavelengths, and now we want to basically route them across a network like this national network across the US. And so a question is, how do we connect Seattle to New York City, right? I can choose this red path through the network over here from Seattle to New York City. I might also choose this blue path and come down around here. It looks like it's a longer distance, but maybe it has better transmission properties. It turns out that it's not as congested, and so there's less nonlinear effects going on between the channels or something. Or there could be another route here. It's so there's many different routes that I can take through the network. And so we call this wavelength routing when we try to select which path to take through the network. And often we talk at routing and wavelength assignment, or RWA. And then more recently, we've been changing the width of our signals, or our wavelengths, and we assign different amounts of spectrum to them now. So we talk about routing and spectrum assignment instead of wavelength assignment. So quantum signals. So okay, I'm not going to go cross country anytime soon, but here's DOE and NIST in the Gaithersburg area, right? Germantown there in the DC area. You could imagine that maybe you want to connect quantum computers between these two locations, right? And so here's the fiber, the red lines of the fiber connectivity between those sites. And so which route do you take? Obviously, there's more than one, even more than two. There's several different routes that you could take to get over there. And so the question is, how do we do wavelength routing for quantum networks? Now, when we talk about wavelength routing in an optical network, one of the main things that we worry about is wavelength continuity, because we don't have wavelength switchers to be analogous with what used to be time or frequency switchers in the old switched electronic networks. But today we call those wavelength converters, right? So we don't have wavelength converters. So you can't take an optical signal at one wavelength, put it into a nonlinear thing, and shift it over to another wavelength. Now, many of you are saying, oh, yes, you can. I've done it in my lab. Well, you can do it in your lab just fine, but no one does it in commercial systems today. So there's not a commercial solution for that will work in communication systems today. So that's an important constraint, and it results in something called wavelength blocking that we'll talk about. There's also no closed loops. You got to be careful that you don't end up creating a loop. Or actually, with an amplifier in the system, you can create a laser across one of these systems. You also have timing jitter that you have to worry about. So you have this synchronization bits in the header. You have accumulation of amplifier noise. So you worry about your optical signal to noise ratio. You have the nonlinear fiber response. You need to take that into account. And we actually know very well how to model that. And so we can estimate what that's going to be. And then the dispersion and polarization. Now, typically today we have a coherent receiver that allows us to measure both quadratures of the electric field. And because of that, we're able to compensate for these effects. Would love to do that in quantum, but if you simultaneously measure both quadratures, you typically kill whatever quantum state that you have. So you can't use the measurement to do the compensation and do digital signal processing. So that's kind of an unfortunate thing. And there's various dynamic effects. So here's a little 6-node network connected by these amplified links. And so we're going to do routing and spectrum assignment. Normally I have some animation on here, but imagine the red line here going across is one wavelength that I'm going to route from node 1 over to node 6, add it in and drop it over there. And but then if I have another wavelength that's going from node 3 to node 5, here I'm showing it in green, but if that was at the same wavelength as the red one, I'd have a problem. I'd have interference between those two. So basically by adding this signal from 3 to 5, I block that wavelength along that link. And now you can't use that wavelength to route any other signals like my red signal from 1 to 6. I have to put it on a different wavelength. And we have to maintain, again, this wavelength continuity end to end. So this is it's kind of the game that we play for wavelength routing. And then you add many different constraints associated with the basically costs to optimize your routing that might be related to the amount of impairments that you're going to generate. So you want to minimize the impairments, maximize the capacity, minimize wavelength blocking is one of the key things that we often deal with in these types of systems. Now, I want to talk about a really interesting quantum system that people are starting to work with here that kind of uses wavelength in a similar way. So spontaneous parametric down conversion can be a broadband source that generates photon pairs. So typically there's signal and idler pairs. So you have a pump come into a nonlinear crystal, you get these signals and idlers, and these will be entangled pairs. And they'll typically obey a relationship where I have my pump frequency, and then the signal and idler frequencies need to add up to the pump frequencies, right? So there's a relationship between the wavelength. And so if we plot the spectrum of emitted photons from an SBDC source, it looked sort of like a Gaussian function like was shown here on the right. And typically if one of my entangled photons is at, say, channel 80, right? So it's offset from I guess the center here is around 100. So and these is channel index. So this is frequency, basically. I'm not sure what the frequency spacing is, but let's say channel 80. And then the other one would have to be on the opposite side at channel 120. So if they're the same frequency, then they would be right at the middle at the peak there. And then as we move away from that central frequency, then they have to balance each other, basically. And so you have this interesting relationship between these entangled photon pairs where they're correlated in frequency in this way. And so now what I want to do is I want to send those around to different nodes. And so we heard yesterday in Don's lecture about different ways to distribute entanglement in a network, right? And we talked about a source in the middle type of link where I have this EPR source, which would be the SBDC source, let's say, that generates these entangled photons, and then it sends them in different directions to Alice and Bob. And then Alice and Bob are going to do some type of entanglement operation that will entangle the memory at Alice with the memory in Bob using the entanglement of the pair that's stimulated, right? That might be some sort of Bell state measurement together with the photon that you get from your memory or something along those lines. It depends on the memory technology that you're talking about. But in general, we have some sort of pair source that's generating this entanglement in the network and then sending it out to these different memory nodes. Now, we can also have a measure in the middle where basically I have some quantum memory, I stimulate it and then create an entangled photon. And then if I send these photons onto a Bell state measurement device somewhere in the network, then I can create entanglement between Alice and Bob, right? And then there's something that I'm referring to as the hybrid scenario here, where, well, I don't have to do this in the middle, right? So in either case, I can put this Bell state measurement at Alice's node or at Bob's node, or I can move that EPR source over to one or the other. Right now, let's say I take the case like I'm showing here on the bottom where my pair source is over on Alice's nodes. So one of the pairs needs to be sent across to Bob. The other one can be kept locally. Now, if you're using a memory, so you can then create entanglement with that memory, and it'll store that entanglement. And then at a later time, Bob will get his photon, and he'll create entanglement then with Alice at that later time. As Don was showing, that depending on whether it's a young or old memory and things like that, it can greatly impact the efficiency of your system. But so maybe you'd like to have it in the middle to keep your efficiency up, but we don't normally have middles to links, let's say. Okay, so you have to put things at nodes where you can put equipment and so forth. And so you might have a scenario like this. Or, well, let's look at this some more. So the other interesting thing with the SBDC sources is you can have single sources where basically now I create these pairs and I can demultiplex them into various signals and idlers in something like a wavelength selective switch. And now I'd have these pairs on different fibers, and I can send them to various nodes around the network, right? Now, there's another approach that people are looking at where you take two SPDC sources, and then you have this Bell state measurement arrangement in the middle, where it's a wavelength selective Bell state measurement. And if you do this right, you can come out with a situation where now you have wavelength selected and entangled and heralded photons that are entangled here. So on the left and the right of this source now, I'll get an entangled photon spitting out that each of those photons has to be at the same wavelength, because I've heralded their wavelength in this wavelength selective Bell state measurement in the middle. And I've kind of I've done an entanglement swapping effectively to create entanglement between these. So in this dual SPDC source, which is part of the zero added loss multiplexing architecture that Dirk Englund and Saikat Guha and others have developed, you're basically creating entangled photons at the same wavelength that are heralded now to go out across my network. And so then we can route those across the network. And it's still an SPDC source. So, so you're going to be able to send that around. Now, let's take a look at what these different sources look like in terms of networks, right? And this is why I wanted to introduce this here, is that there was this really nice work that was presented back in 2018, where folks showed that if I take a single SPDC source, that's what showed on the left here, this source state preparation, and then I kind of demultiplex it, and then remultiplex into various groups going to different nodes. Basically, I can divide my SPDC spectrum, which is shown in that's figure A down on the bottom left. I can divide that into different wavelength bands or channels, kind of like my WDM channels. And I have these kind of channels of entangled photons, and now I can distribute those to these various user nodes around the network. And in this case, they were showing that we can do QKD, and I can have a certain secure key rate among the different users, and offer essentially QKD services among different nodes using this kind of entanglement scheme with the SPDC source. And I can also use it to entangle memories and do other things, right? So this is a really interesting networking problem now, where I have these broadband sources with various wavelength channels of entangled photons that now I need to distribute around the network to my various nodes. And we've been looking at how can we construct different node architectures. For example, this is a single SPDC on the left, where I take my signal and idler and I put it into a wavelength selective switch to divide it up into a bunch of channels. And then I can send them out across the network, again, using wavelength selective switches to choose where I'm going to send them and in which direction across the network. And you can do a similar thing with the dual SPDC source. It's a little bit more complicated, and you have that heralding in the middle. And then in each case here, we're showing this would be a color center type of memory in a cavity arrangement that you could use to store, but you could use different types of memories. It's agnostic to the memory, basically. But you'd often need this MC here would be a mode converter in order to convert over to match the cavity that you're putting into the memory. So there's other details that'll depend on the memory technology that you need to take into account there. Okay, so now if I take the source in the middle approach, right, and I want to look at a network and start to route entanglement around the network, well, let's take our little 6-node network like we were showing in the classical systems, and instead of, again, there's no middles to my links. I have nodes, and I got to put my hardware at various nodes. So I could imagine putting the entanglement source at node A here. And then let's say that nodes B and F want to be entangled with each other, right? So you want to entangle memories at nodes B and F. So the interesting thing is now I need to route through the network one of my entangled photons over to node B and the other one across the network to node F. And well, in this simple network, it's easy enough to do, but in more complex networks, it's an interesting problem to figure out what's the most optimal way to route these across the network. And it's also, it's interesting for this type of architecture, these two nodes, B and F, they want to entangle with each other, but your entangled photons don't go between B and F, right? They go between A and B and A and F, right? So, of course, as I mentioned, if you use that hybrid approach, so you could locate the entanglement source at B, and then you would have the entanglement photons going along the same path or going on a path between the nodes that are trying to entangle with each other. But you don't have to do that. And in fact, you might be able to do things more efficiently if you're putting your entangled source in the middle rather than having it located at one of the two end nodes. One of the things that folks are studying today. And part of the reason that this is really interesting is because there's a number of groups that have done this experimentally. So I showed the Węgorowski paper there earlier. And this is work by a group at the University of Bristol where they've been actually constructing different network topologies. So here they have a multi-node network, and the little figure on the bottom there shows all the different types of topologies that they're able to realize between different end nodes wanting to do QKD with these entangled photons. And in the spectrum here shows kind of the top of that SPDC output curve. And then they have all of these different channels, the different colored bands that they've identified there. Now I put on as an example, you could take various sets of these channels as bands and say that this set of wavelengths is going between nodes 1 and 4, this other set of wavelengths between nodes 2 and 3, another set of wavelengths between nodes 3 and 5. And then you'd have a similar set of designations for the idlers on the other side of the spectrum, right? And so now you want to decide on a routing algorithm, and this is a great problem where it's kind of within the wheelhouse of what we do in classical networking, right? We're routing wavelengths around a network, but there's a whole new set of constraints here in these quantum sources to work with, and we've got commercial systems that we can use to realize and make measurements on these systems. Okay, so Zoom poll here. So which of the following is always true for routing SPDC? Sorry, I just blocked my message here. SPDC-based both ZOM and single source entangled photon pairs through a network. So which of the following is always true? The frequency of the photons must sum to a frequency determined by energy conservation. The photons must travel different paths. The photons must arrive at their destination at the same time, and the loss of either photon will fail the attempt. Okay, well, folks are answering this. I'm going to answer. There's a question here that a lot is dependent on the SPDC source being very bright to be transported, repeated, mode converted into the memory. Actually, we're not considering repeaters here yet, and have to deal with that. This is all kind of single hop entanglement, which is interesting, and it kind of works. Now, it is tricky to be mode converted and to get it into the memory and so forth. But if you're just doing QKD, that actually works quite well. Generally, you're not coexisting with classical channels in these types of networks either. So, although that could be something to look at, right? Okay, so I'm going to end the poll here, and so the actually, I just realized that I think there's two right answers to this question, and I think you guys figured that out as well, right? So the always true for routing SPDC sources. So, well, for sure, loss of either photon will fail the attempt. That's always true. Oh yeah, so that is the correct answer. So the other one that people answer is that the frequency of the photons must sum to a frequency determined by energy conservation. Well, that's true for the single SPDC source, but so it's a trick question here. So in the double SPDC source, they don't sum to the value determined by energy conservation. In fact, in the double SPDC, they're at the same frequency. All right, so okay, a little bit of a trick question there. So, But for sure, the loss of either photon will just fail the attempt. Okay. So I think we share the results there. Yeah. Okay. Okay, so let's move on. Okay, just I want to talk a little bit about, I don't want to get too much into the weeds of these classical systems, but as I mentioned before, in these classical systems, we use coherent receivers. And you say, well, how do they deal with all the polarization issues and the jitter and all this kind of thing, right? And well, the answer is that your signal comes in and you split it with a polarizing beam splitter, and you simultaneously measure both polarizations, and you measure both field quadratures. So you measure everything about the electric field, and then you put it into digital signal processing. And because you've measured everything about that field, okay, you're able to measure any linear effect you can determine quite well. So group velocity dispersion, polarization drift, polarization mode dispersion, and frequency drift and so forth. Any single channel type effects, especially linear effects, you can compensate in digital signal processing. Now, nonlinear effects between different channels, if I'm not measuring that other channel, I don't know what it is, and so I can't. And also, nonlinear effects depend on where you are along your path. And so, because I don't know necessarily what happened in the middle of the network, I can't necessarily determine exactly what the nonlinear impairment is. But any linear impairment, I can determine quite precisely. And so we deal with all of these polarization problems and everything with digital signal processing. In quantum, we cannot do this at all, right? Because as soon as you try to measure both polarizations, both quadratures, you've measured everything about your photons, and you have no more entanglement, right? So just to say that what we do in coherent, we can't do. And there's also, we do something called intradyne. So not just homodyne and heterodyne, but intradyne means it's between homodyne and heterodyne, where the signal is offset from the local oscillator, but just by a little bit and still within the bandwidth of the receiver. And that allows you to do, with fast digital signal processing, you can track signal phase and frequency variations and so forth. And this would be an example of a coherent transceiver. And basically, I won't go through the details on this. There's a number of references for this, but there's a lot of digital signal process, layers of digital signal processing and forward error correction coding that we're using to compensate for this. And it's good to be aware of that. And then these are examples of constellation diagrams. So a QAM signal has different amplitudes and phases, and you define these constellation points. So the plots here are mapping out amplitude and phase. So if you go away from the origin in the middle, the farther you are from zero is a higher amplitude or intensity signal. And as you go around the circle here, you're changing your phase of your electric field, right? And so we can define different amplitude and phase points in phase space here as our different modulation points. And so you can see, if I have this in the upper left-hand corner, it's a 16 QAM signal with 15 dB OSNR, where I just had, basically, I added noise to it. So you've got these noisy constellation points. But when I have nonlinear phase distortion, then these constellation points start to smear. And nonlinear effects means you're more sensitive to high amplitude, right? The nonlinearity is in the amplitude or in the intensity of the signal. So the points that are farther from the origin, they're smeared even more. And this really nicely illustrates that, yeah. So you can see, so that's the sort of thing that these classical signals go through. And then basically we, as a function of distance, you can get a longer reach or longer distance and be error-free, basically, if you have a smaller spectral efficiency. So as I add more constellation points, I get higher spectral efficiency, but then I'm more sensitive to noise and nonlinear effects. And so I can't go as long distance. So generally we have this relationship between the distance that I can transmit my signal and the spectral efficiency of my signal. And these are kind of things that we play with in the classical space, right? And then we'll go over a little bit the switches. So I think the switches are an area where we have the highest potential for using things in quantum, right? So when we talk about a wavelength selective switch, the best way to kind of get a mental picture of this is there's this very nice figure. This is from Dan Marone. This was one of the early wavelength selective switches he made many years ago, where it's kind of this piano type of switch. So these are mirrors, and so you can see how you can tilt the mirror down like that. Um, and so if you divide up your signals coming in on the fiber from a grating and put them onto these mirrors, each mirror could be a different channel, and then you can tilt the mirror in different and then send your light to a different output fiber, right? Now it turns out that today we use a liquid crystal on silicon technology in most commercial wavelength selective switches. So it's a little bit different technology than what we're showing here, but it does effectively the same thing. All right, so you can think of it this way. Now, so you have this linear array of mirrors effectively in these wavelength selective switches. Now, what's interesting is if you look at the losses through one of these switches, normally on one end of your array, you're going to have fairly low loss, like 3 dB loss. But then at the far end of the array, it'll be a 7 dB loss. And the way that they're architected internally, you just get higher losses at one end of this array, and it's because of how the optics are laid out and the way that works out. Now, these haven't been optimized for low loss, especially because I have amplifiers all over my classical network, so I want it to be reasonably low loss, but I'm not going to work too hard to get that. But it's interesting that so these wavelength selective switches, they can be used for quantum signals. If you use them for quantum signals, I recommend that you use the portion of the spectrum where you only have 3 dB loss and not the 7 dB part of the spectrum, right? And the spec just tells you that the loss is 7 dB, and that's the conservative spec. It's guaranteed to be below 7 dB, but you can get down around 3 dB, so very low losses there. And it'd be interesting if people started to develop new types of wavelength selective switches that really tried to expand this low loss region for these wavelength selective switches for quantum signals. That would be interesting. So fiber space switches are very common now, developed about 20 years ago, and you can get very high port counts with them. So this is the Caliant 320. It's 320 by 320 fiber switch, basically. And so you can put massive amounts of data through them, as much data as you can fit into a fiber, right? So basically it's fiber to fiber, the whole fiber is being switched, and they use MEMS internally. Now the worst case loss in a switch like this is 3.5 dB, so that's quite low. And in practice, you have many that are kind of 1 to 2 dB. If you just connect two fibers together, you're going to have a few tenths of a dB loss. And in fact, if you say, what's your worst case loss, it might be a half dB or something, right? So so just the connector losses alone are already sort of a half to 1 dB kind of worst case scenario. So there's not much going on with the switches. Now, generally, these are MEMS-based switches where you have these types of actuators where you can tilt in different axes, right? So and you're going to tilt and point them to the different output ports. And there's what we call 2D or 3D MEMS switch fabrics. So the 3D, you can see you come in, you reflect off one mirror, and then go over and reflect off another mirror, and then go on to the output fiber array. And so with these two mirrors offsetting each other, you're able to precisely align from one fiber to another fiber. And there's a compartment inside that box that basically has these arrays of mirrors, and they're facing each other, and they're doing the switching. With the 2D case, well, I should say with the 3D, you have to very carefully tilt and align, and you have to hold the mirrors in a particular position in order to, and you try to optimize it for lowest loss to get the best coupling into the fibers or between the two fibers. In the 2D MEMS, it's an on-off type switch, and actually sometimes you use it for diffraction, not for actually as a mirror. So you can create on-off diffractive elements this way. But the great thing is, if with the 2D style, I don't have to hold a mirror or the element. I don't have to hold it into position. It can slam against some barrier, and then the other way around. And so what happens is you can make 2D MEMS work much faster than the 3D because I don't have to hold them in place. I can just slap them back and forth between two different positions. And so that plays out in kind of the resonant frequencies and how these work, right? So if you look at the sort of a single axis switch, and if I have an analog type switch where I'm holding the position versus the digital, which I'm just going on off, right? So in the on off case, or the 2D case, I can get much higher speed switching. So the resonant frequency is kind of the limit at which I can switch at, and I can get up to tens of megahertz switching speeds with this. Whereas if I have to hold the position with an analog voltage style, continuous analog voltage, I can get very high port counts, of course, with that. But now I'm going to give up on my speed. So there's a trade-off of speed and port count with these types of switches. And you'll see that with the dual axis as well, right? So, so you're going to have that trade-off. And that's something that's important. If we want to do switching with quantum signals, I want to use these low loss types of switches. I need to figure out what type of switch I'm going to use, the digital or the analog control, and then and what sort of port counts I want to go to, and speeds I want to get at. And then I want to mention that you can think out of the box, and that's what Ming Wu did at Berkeley, where he developed this MEMS switch that's a paddle that has waveguides on it. And when the paddle goes down, so you can slap it down, you can do that very quickly on microsecond time scales. You basically actuate this this waveguide, and you get the crossbar connection. Whereas if the paddle's up, there's no connection there, and the signal goes straight on through. And this can be made very low loss. So this was a sort of exciting development where you could make a very low loss crossbar switch using this kind of MEMS paddle arrangement with microsecond speed switching. So I think there's still a lot of opportunity for kind of novel switching architectures and these types of chips, and we need to develop more of that for quantum signals for sure, especially for low loss. Okay. Maybe why don't we just take well, let's see, are we going to 7 or 7:30, Brianna, I guess?
30.
All right, so, okay, 7:30, okay, good. So, all right, so why don't we take a 5-minute break? I'm in Ireland right now, so it's 6:40 p.m. here. We'll go to 6:45, so a 5-minute break. We'll come back and we'll do, this is kind of getting to the final section of this. Okay, let's get started again here. So network control and management. So let's get into this a little bit here now. So we talk about optical system control and management. So when we talk about a control plane here, these are software controls that actuate system functions, usually in real time and often through autonomous or automatic controls. And we talk about an IP router control plane. So the IP routers, they automatically tune and adjust and figure out neighboring addresses and this kind of thing, right? So that's often when people talk about a network control plane, the kind of quintessential one would be your packet router control plane. There's a management system. So your management is the operator interface for what we call offline management functions, such as maintenance, provisioning, fault isolation, and often you'll set the policy for the control plane operation in your management system. And then if you'll hear terminology like intelligent optical system, cognitive optical networks, programmable optical system, agile optical networks, software-defined optical networks. These all refer to some form of automated or autonomous control plane operations for optical networks. And but current commercial optically amplified systems are all statically provisioned. So we're not doing switching. So you're controlling kind of the static, what we call provisioning of the wavelengths across the system. Okay, so and early on we mentioned layers, and the other day Don talked a little bit about layers. So often people talk about this OSI model of layering, where you have your layer 1 would be your physical layer, then your data link layer, layer 2, your network layers 3, transport layer 4, and then there's a bunch of application layers that I usually don't know anything about. And then these correspond to typically the optical layer, Ethernet or OTN layer, the IP or packet router layer, and then there's TCP, and then your application services are above that. It's important to point out, and I should mention that there are many people who consider OTN to be layer 1, and they've branded a new layer, layer 0, and they call that the optical layer. I always think of the layer 1 as optical or physical layer, but different communities have different definitions here even. But it's interesting that in the classical world, so this physical layer is where the optics is and the optical systems and their control. And then above that, everything else is electronics. These are Ethernet, OTN, even that OTN is optical transport network. That's electronic switches with optical transceivers plugged into it, right? So, but everything, all the switching associated with that is electronic. So, so that's all electronics. And then above that, applications and services is really just software running in a server somewhere, right? But these electronics is actually electronic boxes, chips that are doing something in there, right? So, and each one of these layers, especially layer 1 through 4, will have a control plane in which the corresponding protocols for that layer are executed. Network management would provide an interface for the network operators to tune the controls within each layer. And the layers should operate independently, and the layers should allow for independent technology development. And generally should only use layers if you need them, okay? So in the classical world, so people who work on optical systems in the physical layer often know little or nothing about Ethernet and packet switching and things like that. When I was a PhD student, it was all just a mystery to me, and I'd see these clouds and these boxes with words in them that just meant nothing to me. Over the years, I've learned more and more about the higher layers, but really, you know, so you can spend your whole career working on optical systems without knowing anything about Ethernet and packet switches, and vice versa, right? There are people in the packet switching and people work on TCP and things like that. They have absolutely no idea what the optical system does, right? And that's an interesting thing about layering, and it's a really valuable thing that people can specialize that way, and you can develop that technology independently. And that's a very powerful thing about layering that we should keep in mind as we think about layering for quantum networks, right? Another thing that's helped me in terms of thinking about layers is I like to think about an actual physical box, and I'd see all these pictures of these layers, and it just what does that correspond to? Is that real? And so this is one way of looking at it, is that basically, especially for the first 3 layers, let's say, so layer 3, you actually have a packet router, which is a real box. And it's going to send its information into an Ethernet switch, and it's going to be a client for an Ethernet switch, and then the Ethernet switch will send its information into an OTN switch. And so these are each boxes, and then the OTN switch will basically send it to an optical system with the transceiver, and then you'd have your fiber connection, and that would connect across. And so when people draw a layer 2 virtual network or a layer 3 virtual network connecting packet routers or Ethernet switches, the only real network is the fiber network, right? And the connectivity between packet routers and Ethernet switches is what we call that virtual network. And basically each of these boxes, as they put their data into the next box, their data becomes the payload for the next box, right? So So the IP packets, the Internet Protocol packets, are the kind of application or payload data for the Ethernet switch. And the Ethernet switch puts its header onto that data and then sends it to the OTN switch. And then the OTN switch puts its header on there. So another way of thinking about these layers and these boxes is that with each layer, you're going to put another header in front of the data, right? And so you're going to keep encapsulating and encapsulating these different things. And in each one of those headers, you have the protocol information that tells the box what to do with the data that you're sending it, right? And then it passes it along. And that's kind of how these layers all hang together and how we use them and how the different layers talk to each other, right? And I should say that, and then today, the OTN switch and this, what I'm calling the optical transceivers, these are kind of the same box now. And actually all these boxes have been merging together. So these days you can buy a packet router that's also an Ethernet switch, that's also an OTN switch and has line side optical transceivers plugged into it. Okay, so it's a little bit blurring, but there was a day when you had a separate box for all of these things. And we try to simplify and put more functionality into boxes and stuff. Now, when people talk about software-defined networking and layering, so SDN is really a tool to work across layers. We talk about a northbound interface and a southbound interface. So northbound interface would be an interface to an application. And suppose that you have some application that needs very high capacity or wants to change how data is sent between two end nodes, right? So this is what SDN is for. So it's that northbound interface allows an application now to change the routing tables for the routers or change the configuration of the Ethernet or optical systems. And the southbound interface is what talks to these boxes down here. Similarly, often SDN will allow a network operator or other advanced users functionality so that they can come in and they can program these lower layer boxes, basically change their control planes, kind of like a management function. In fact, a lot of systems, what they've done is they've taken their management interface and made it an SDN interface and gave it a northbound interface for network operators to interface with and so forth. And often it's from that application layer down, but also there's a lot of interest in like IP routers being able to talk to optical systems. So IP routers, if there's a lot of congestion, they can't do anything if they don't reconfigure the physical connections, right? So if there was a way that an IP router, when it detects that there's enormous packet congestion, its buffers are filling up, it could send a message then to the optical system and say, put more capacity on this link, switch this optical signal over here. And then you could release a lot of that congestion. So there's interest in doing this sort of thing. And one of the things that this points to is that when you do this layering, well, it simplifies and allows you to innovate the technology well, you also give something up with it, right? And so there's certain efficiencies and capabilities that you surrender when you create this layering. And so as we've introduced concepts like the software-defined networking, what we're doing is we're saying that the layers are broken, and we're coming up with a technique that allows us to now fix it by putting in this added functionality, and so and gain greater efficiencies. And I put this in here just as an example. So this is an SDN control plane that we developed for an optical system. And basically we have different layers of controllers where we have an orchestrator that has the user interface or application interface for its northbound interface. And it's kind of looking at the broad overall network, and it has things like a repository with information about the network, and it has connection control and management, the path selection. So how do I figure out the path through this very large network at a certain level of abstraction? And then the local controller would be for a certain local domain or network domain. Again, Don yesterday talked about network domains. And so you'd have this local controller running within a single domain, and it's optimizing and choosing the path through that domain. And so the orchestrator is kind of making a path of paths, whereas the local controller creates the local path and controls the elements there. And this, what we call the agent, is the thing that talks to the actual network device and does the actual information and so forth. And so you can imagine that this kind of structure will be important for controlling quantum systems. And the question is, what type of elements do we need in here in order to control our quantum systems? And so what does a control plane for an optical system look like? You won't find a lot of literature on optical system control planes because in general they're proprietary. So the optical system vendors, that's their secret sauce. They don't publish a lot about it. And more and more as we've moved to AI controls and what we call data-driven techniques, it's starting to open up and we're getting more visibility into these systems. But this was when I was at Bell Labs and we were working with our product groups and helping them to develop the kind of physical layer control plane. This was actually something that we got to publish, and we developed an algorithm for basically adjusting the optical powers around a network and showing how you can do that efficiently. And we had a system of sort of adjusting channels and freezing out the control of certain channels so that you didn't have interactions between them. And so I guess the point I'm trying to make here is that we're going to need control planes like this for quantum networks. It won't be doing the same thing as this where we're controlling the optical powers of these WDM channels, but we'll need to control the paths of the different quantum channels. Maybe we'll have to detect whether the losses are getting too high, if my rates are getting too low. And there's a bunch of control and stabilization operations that we'll need to do in a network context and make this work. And there's a lot of research yet to be done on that. I talked before about RWA and provisioning. How do we connect Seattle to New York City, right? And basically, we use this quality of transmission or signal to noise ratio estimate to choose the route and wavelength. That's the bottom line. And so what do we have to deal with? Why do we need to look at the signal to noise ratio? Well, this was an example where we did some work with folks at Microsoft and were able to publish data on their commercial system, and it shows the signal to noise ratio as a function of wavelength on different routes, and you see this wide variation in performance that you get. And then, so that's as a function of wavelength and route. And then if we look at it as a function of time, you see that the signal to noise ratio is bouncing up and down, and there's these discrete jumps where someone changed the switch or did something in the network, right, that created that kind of discrete jump in there. And so, so you have all of this going on inside the network, and that's what we have to contend with the control plane for these optical networks and figure out how we can guarantee that the signal to noise ratio is going to stay within the proper range and not create errors that will disrupt service, basically. So a generic sort of wavelength provisioning protocol, and again, every vendor would have their own protocol, would be you get a connection request between nodes A and B. You'd run this routing and wavelength assignment algorithm to determine the route and wavelength. Now you need to estimate the quality of transmission, or typically that's the signal to noise ratio of your signal, to ensure that this path and wavelength meets whatever performance requirements you have. And then you go through a provisioning operation where you're going to gradually open up the channel for the first link, adjust your amplifiers and optical powers, then open up the second link and the third link, and you might be freezing out controls on other signals while you do this. And so there'd be this very complex step-by-step operation that you would take and then you get your final bit error rate for your end-to-end connection. And then you let that soak for days or weeks before you actually put live traffic on. Right, so that's how you switch a wavelength in a metro or long haul system today. Now they're working on automating that more, getting to work more rapidly and things like this. But that's a research problem today, is how to improve this protocol. So the functions for optical physical layer controls. And I'm focusing on the optical physical layer controllers because quantum systems, ultimately their control, the main control is going to be an optical physical layer control, right? We need to figure out what this is going to be and how it's going to work. And so there's a whole bunch of different functions, provisioning channels, tuning amplifiers, tuning channel powers, managing faults, tuning and controlling transceivers. And in fact, most of these we don't do today. You can find papers on them where people have studied real-time route selection, real-time optical circuit switching, things like this, but it's still not in commercial systems today. So it's an area of active research. And then this would be an example of when we try to put it all together and we have these controllers running across multiple network domains, and you want to provision a path from one node through the network to another node, crossing between two network operators domains, and we have the various local controllers and the orchestrator that I mentioned before. So how do we route these wavelengths through different internet service provider networks? How do we guarantee signal performance? How to scale control operations across domains? Okay, so then for quantum, right? So similar control and management issues for quantum networks. If I want to route a quantum signal through this network, how am I going to guarantee that I'll get a certain entanglement bit rate per second and that meets the requirements for whatever quantum computation or operation that I want to do in the network? How do I get it to work across different network operators, domains? I think Don was alluding to this also yesterday a bit. So the layers in quantum networks, so coming back to this, it's still an open question how to define these layers. And there's been some nice work where people have introduced some layering techniques. Often the layering seems to be associated with some sort of functional operation. So attempt entanglement generation, make the link robust, and then do long distance entanglement across a network. All three of those that are identified here for the physical link and network layers there, that's what an optical system control plane does in the physical layer control. It attempts the connection, it ensures that the connection is robust, hop to hop, and then it also makes sure that you can get connections over long distance, right? So I'm not sure why we want to divide those up into three different layers, or if it even makes sense, right? But it's early work, and it's good to try to think about what we might do there, right? And there's also the difference that as I mentioned before, in our current classical layering, the optical is the physical layer and everything else is electronic. So there's a natural division there, right? And the question is, what are the algorithms that you're running on these different layers, and why do you need a different protocol that would talk that? Now, there's been some other work, as Travis Humble's work looking at SDN for modeling in quantum systems and some simulation work there. It'd be really interesting to see more work on SDN and how it can be used as a control plane. We don't have to go back 20 years to the layering model that we used before. We can jump straight ahead to software-defined networking and figure out how we can use that. There's also, well, here's the example where, and this is some really nice work, but looking at a physical layer and a link layer. And so you've got scheduling in the link layer and various operations going on in the physical layer. And we need to do more thinking about what's the right split to take here, and what are the protocols that we're doing there. And it's really early days, I think, for this type of work right now, and what we should do. Okay, so a Zoom poll here. Okay, so how many layers will quantum networks need? There's no wrong answer here, obviously, right? So no idea how many they will need. 0 layers, maybe 1 layer. I don't know what the difference between 0 and 1 is, actually. 7 layers, maybe too much. 4, I don't know. Ultimately, I think it's going to be driven by, let me go ahead and end the poll here. I'll take a look and see. A lot of people said 4, which is a reasonable kind of answer, right? One thing for sure is, in the computing space, we need to run these circuits, right, independently of what's going on in the underlying network. And so you can certainly see a layer there compared to the physical network. The hard thing is that quantum networks, I mean, the network is the qubits, right? It's all tied together in a way that it's really hard in my mind to split out among layers. But there's probably a couple of layers that you might define there, and especially to get us started, we need to simplify things somehow, right? And that's one of the functions of layering early in the optical internet days, was to create layers to simplify the engineering, right? Okay, so the last section we're going to go through here is on field trials and testbed experiments. I just wanted to give an overview of some of what's been going on in the quantum space and relate that to field trials and testbed experiments in classical networking. And as an optical networking guy, I go back to the early field trials in optical networks, and one that's particularly well known, especially among my generation, was the Monet network, which its project started in 1996. If you remember, the big boom in telecom was in 2000, right? 1999, 2000. So this was a project that a lot of people say helped to create the boom. It was one where they basically looked at a whole bunch of really advanced technologies. And they created a mesh network. They had it was the first time that they're realizing kind of in the field wavelength cross connects, wavelength add drop multiplexers. They did wavelength conversion, I believe, and tunable filters, and all these really advanced kind of networking topics and so forth. But the interesting thing, so that was 96. They did all that. And then all these guys left and went and created startup companies, basically. And what they did was, by doing these very advanced experiments, they figured out, wow, we can make WDM work and really make it scale. And but what they came out with, what they built, this is actually, I should put the reference on there. This is from actually it was Lucent at the time, the Lucent kind of point-to-point Wavestar 10G optical system. And it's basically just a point-to-point WDM system. But then they basically learned how to really make this at scale, and with 6 fiber spans. And if you were looking at that big hero experiment of the test bed, you might be disappointed to see such a simple, basic point-to-point system. But actually, so what happened was, so here are some of the key technologies from that Monet experiment. So we had acousto-optic tunable filters. It turned out those were never used, and it was kind of a bad idea from the beginning. But coherent transceivers. So we had coherent transceivers back then. Turns out they didn't get used commercially until 20 years later, right? Wavelength cross connects and add drop multiplexers also weren't in those initial systems, but they returned 10 years later, especially as we developed wavelengths like the switches, which is an important technology to really make that work well. Tunable transceivers also were used in the test bed, but didn't appear commercially until 10 years later. Mesh networks, 15 years later. And space division multiplexing is now being used on multiple parallel fibers. So what happened is it really pushed the envelope forward, enabled something that's much simpler to find commercial viability, and then created a roadmap and a pathway to evolve to all these advanced technologies. And that's what we've done over the last 20 years, is basically introduce these various technologies that were done in that early hero experiment. And we've had basically test bed experiments and hero experiments like that happening throughout this process to basically push the technology forward. And that they play a very important role in technology development. Yeah, there's with QKD, there's been a long history of field trials, right? So I think the first were in the 1990s, BT again there. But there was this nice work in China that just blew everyone away, right? So this is, talk about impact that really got everyone's attention and working in quantum here. So basically, this kind of large scale QKD network, both satellite and terrestrial network, deployed and realized across China there. And now in the EU, there's a Euro QCI program where they're going to create an EU-wide QKD network across all of the EU and really connecting up all of the sort of government offices and medical facilities and places that really need the QKD capability there. And so we're seeing this explosion of activity through a series of test beds. And there's a review in this Optics Express paper 2018, which is a nice one to take a look at, and if you want to see that. So again, the power of demonstration and hero experiments, right? Really interesting in the QKD space, there's a transmission reach race that's going on, right? Where these twin field QKD capabilities have enabled folks to go out to hundreds of kilometers. And so there's a 140 dB loss, 834 kilometer QKD transmission experiment that actually I pulled out. I thought that was the longest distance. Then I found the other one in 2023 here, 1,002 kilometer QKD experiment. So you've got to pay attention. They're coming quickly here. And now you can see that when they go out to 1,000 kilometers, the secret key rate is 10 to the minus 11, right? Bits per second. And well, here it's, so 800 kilometers, 834, and you're getting a secret key rate 10 to the minus 2. So they're miserably low rates, right? But again, it's a hero experiment. It's pushing the envelope in the technology. What will actually get used and deployed in commercial systems will be the much shorter reach type of results. But we need to do the research and really push the envelope this way that's happening there. And it's really good to see. And this is something that would go on all the time in the classical networking space, where there were races to get long distance coherent transmission and high capacity coherent. And then there was, when EDFAs and WDM first came out, they were trying to do more and more WDM channels over longer and longer distances. And that's really moved the technology forward in important ways. And whether you think QKD is an important technology or not, it's moving the technology envelope for quantum technologies forward in important ways that shouldn't be overlooked. So here's an example of a metro network demonstration where I point to this one because it's a coexistence experiment between QKD and a commercial, in this case, a Huawei based WDM system deployed in a field trial over a network in Spain, Telefónica's network, and a commercial network, and really showing that you can make these QKD systems compatible in the same fiber now they did have to turn down the classical signals here. It's a short reach metro system, so they could tolerate lower power on the classical signals. Interesting experiment there. I mentioned the use of SDN, so there have been some groups that are working on SDN control for these QKD systems, as well as more recently in the entanglement-based type of systems. Hollow core fibers, we talked about how they can potentially be designed for very low loss, and they get rid of the nonlinear interactions, Raman scattering. And so there's been Bristol and Southampton has been really pioneering these hollow core fibers. So they showed entanglement distribution over hollow core fiber and how well that can perform. Multi-core fiber experiments. So this is a nice illustration. I've talked about multi-core fiber a few times. Some of you are probably wondering what that means. Well, on the left-hand side, the lower left, so you have this fiber and it's got these, 7 different cores in it, basically. Each of those little orange dots is a fiber core where you can send light down and get a signal through. And so they looked at, if I send my quantum signal through one core and then I have classical signals going through the other cores, what does that do to crosstalk between the signals and how well that can work? And so that's a nice way to isolate. You still do get some linear crosstalk, but it's down by 50 dB in this case. And then I mentioned there's something called MDI QKD. So that's kind of a new technology. And here is a field trial of an MDI system that the Delft group did using telecom wavelengths across long distances in the field type experiment. And that, I believe, is going into commercialization now. And then just to update, so most recent with these kind of SPDC type entanglement sources with wavelength distribution. So the group at Bristol has been doing experiments with these, and they have what they call their Q-ROTEM, which basically breaks out that SPDC spectrum to create these different wavelength pairs and can distribute them around. And here they show coexistence between entangled pairs as well as classical channel. I forget, this was just reported in ECOC this year, and they had QKD signal, sort of a prepare and measure QKD signal all in the same fiber. These are fairly short reach, although they have one link that goes up to 49 kilometers and a loop back there. But a lot of it, because of the Raman scattering, they're keeping it down around 2 kilometers and so forth with the classical signals in there. And this is kind of where things are in terms of large scale QKD field trial type experiments. Okay, so, and that is it. So we have a number of references here for further reading. Let's see, we got some questions. Maybe I'll answer quickly here. So recent experiments, the scientists managed to span a distance of 3,800 kilometers between a ground station near Moscow and another near Urumqi. Okay, interesting. So yeah, the distances that we're talking about for QKD and fiber, are dwarfed by the distances that you can get in the satellite communications, right? And so it's interesting to explore that. And there's a number of large initiatives in the US and the EU and China and other places where people are developing these satellite systems and starting to look at quantum signals, initially QKD, but eventually moving to entanglement over satellite systems. There was an early question on there. Can you please explain in more detail the isolation loss of DWDM systems? So those wavelength selective switches and so forth, they're basically split out individual channels and put them on different fibers. So they select a portion of the spectrum and send it somewhere, right? But the rest of that spectrum that doesn't get selected, it goes somewhere also, right? And the rest of that spectrum can get scattered within the switch and create kind of background photons that then can get picked up by any of the fibers going out of that switch. And then also some of the residual spectrum can get coupled into the output fiber that you're trying to couple to with the spectrum that you selected. And that amount, so there's always no filtering is perfect. So maybe you filter down 30 dB, 40 dB. I'd say 40 dB would be doing well for one of these types of switches. But the trouble is going down to single photon levels, you need sort of 100 dB, right? So you're always going to have some background light, background noise that's going to get into your systems with these switches. And so you have to be careful about adding additional filters typically. And interesting, if there's more commercial use of switches for quantum systems, there's no reason that you couldn't put extra filtering or even design one of these wavelength selective switches so that it had much higher filtering and extinction of these of the signal. So I mean, you can always put an extra filter on the fiber, but if we want a tunable filter, then I have to cascade it through multiple WSS. So if one wavelength selective switch has a 40 dB extinction, then I can put it through two, and now I've got 40 plus 40, so I've got 80 dB of extinction, right? So you can always play that sort of game, right? So, okay, we got another question just came up. So what about CVQKD? Are they going to be commercially available? What would be the advantage? Well, most of these systems, they use some sort of phase-based QKD, right? So, so that's commercially available today. Yeah. All right. Other questions or anything? I think we're just about at the end of our time now. Shelby, was there anything that you wanted to add here?
I don't think so. I think you covered pretty much all of it.
So so there's a question here, but they still detect single photons in commercial systems. No, not sure what that question is asking. So in the commercial system, so actually they're using highly attenuated laser signals that are effectively what we call coherent quantum states of light, or semi-classical states, and they're typically at photon levels of below 1 photon per time slot, right? And they use this decoy state system where they will change the kind of number of photons per pulse. So it'd be typically less than 1, and it might be varying in different levels below 1, right? So extremely, extremely weak light. Okay, I think that's it then. Thanks so much, everyone. Really appreciate your attention and time. And last thing is that there's a course evaluation survey, so please fill that out. We'd appreciate your feedback on it.